the concepts. And so big data, there are many definitions of big data. Many people have been defining in various different ways. The definition that I like the most is it's a collection of large and complex data sets for which the existing management tools or the data processing tools do not provide the accurate or the needed answers. Okay, so this is just one definition of big data, and I'm sure you'll hear a lot more definitions from all the industry and academic experts tomorrow. Okay, so this is just one definition. But one thing I want to keep it clear is that though the term big data, because of the term big, people think it's often a large volume of data. But in the term of big data, there are a lot of other complexities than just being large or voluminous, right? So some of the complexities include being heterogeneous, noisy, complex, wherein you have data correlations. It doesn't necessarily mean it is large in volume, but there are many other complexities like being streaming data, right? So temporal data, time series data, which is also known as longitudinal data, and so on and so forth. There are many other challenges other than just being treated as a large volume or big data itself, right? So the key component the big data tools or big data analytics algorithms try to address is try to find something that is unknown to the user. So that is key component, that they want to deliver something that is not obvious from the data or not obvious to the domain expert or the end user. Okay, so that is one thing. It aims to answer questions that are previously unanswered. Okay. There are different components of big data. Big data, because I just want to keep it clear at a high level first where we are going towards in this particular tutorial at least. So big data, it's a new concept. It's almost revolutionizing many fields, and there are different categories or the different components within the big data technologies, right? So some of them focus on data capture, so new ways of sensing and accumulating more data, and storing the data, the storage of the data, searching through massive amounts of data. So this is information retrieval. So looking at massive amounts of data as opposed to just looking at 1 million record. We are now talking about searching through almost petabytes or terabytes of data. Right? So then the information sharing, so including privacy preserving issues and sharing of massive amounts of data, so some research in communications and so on. And finally, the most important thing, at least according to me, is the analysis of data, because there are advanced technologies now to store the data, to capture the data, to process the data, but trying to identify some useful knowledge out of the data, of such massive volumes of data, is a upcoming area. So it's an area that is being investigated very heavily recently, and my expertise is in this area, where trying to analyze data of huge volumes, with the goal of getting some useful knowledge out of the data and trying to make some provide some actionable insights about the data, trying to make some useful and actions that can be revolutionary for the future data that we are going to collect. Okay, so some of you might have seen this 4 directions of big data, or what are the complexities in big data. One is volume, so the 4 V's of big data. Volume. Velocity is the streaming data, where the data keeps on coming in. So the volume and velocity are the 2 major issues that people often talk about in big data. But there are also other things which might look simple, but still very in practice it's very hard to deal with, are the variety of the data, which is heterogeneity in the data. In the same problem, you might see data that is of discrete nature, continuous nature, the temporal nature, so on and so forth. So there are many complexities within the same problem. So there is a lot of wide heterogeneity in the data. Right? And the 4th one is the veracity of the data. We want to know veracity is about the truthfulness of the data. Whether we really want to analyze, we want to see how good the data is to make some inference, because everybody can generate the data, but whether this data will be useful in the future to make any useful decisions is about the veracity of the data. So these 4 components together will form a nice big data solution, or a big data for a big data application. Right? So this is just an introduction of big data and what is the challenge. So if we go a little bit backwards and see why we are here, I mean why big data has become so challenging, is because of the data accumulation. So in many applications now, data sensing has become much easier. So sensing, because of the advancements in the sensing technologies, advancements of new sensors, and so now a mobile app can capture many of the activities, either running, walking, or any of the activities that you do on a daily basis. So the sensing has become so cheap and so easy that everybody wants to get more information about a particular patient or a particular condition or a particular object and so on and so forth, right? So sensing has become easier. On top of it, the storage technology have also become cheaper and much smaller. So storing big amounts of data as opposed to two decades back, storing one gigabyte of data was a big deal. But now, even terabytes of data, we can have it in a small USB drive. So storing has become very, very inexpensive. And the fact is, many real-world applications, many scientific, biomedical, all these other applications keep on collecting massive amounts of data. Now that because of these two advancements, everyone has started to store a lot of data in the hope that they will get something out of it in the future. Though they may not have the actual technology to analyze the data at this point, the hope is that we will be able to analyze this data. Since the storage is much cheaper, nobody wants to throw away the data. So data keeps on getting accumulated. So there is a study that was done in 2012 which says whatever digital data that was available until 2010, that entire amount of digital data got doubled in the next 2 years. By 2012, that amount of data got doubled. And so this projection, if it keeps on going at the pace at which the data is being generated and the data being stored, then it's going to explode. There will be a data explosion in the near years to come. I will give you a couple of minutes so that you can just go and sit if you would like, because it's a long 2-hour tutorial. I don't want people to think. So we have some seats over here. Just. So in spite of the advancements in the sensing technologies and storage technologies and the fact that the data is growing, the analytics have been lagging. So analytics trying to develop algorithms to process and analyze the data so that we can get some useful and actionable knowledge out of the information out of this massive amounts of data is still been lagging. So that is the effort that I'm going to emphasize more on, how to develop analytical algorithms on big data platforms. So to do that, I have to first explain what are the platforms and what are the technologies that are available, and then we can address on the analytics component. Okay, so that is one of the motivations is that if you look at many of the scientific applications these days, it used to be hypothesis-driven applications where you build a hypothesis, you test a hypothesis on data. But now, as the data sensing and storage has become easier, it is becoming more data-driven science as opposed to having hypothesis-driven science. So the data is telling a lot story. You might have a hypothesis, but it's very easy now to evaluate whether the hypothesis is true or not. Most importantly, it's easy to build a hypothesis just based on the data that you have seen. So I mean, healthcare, we can get some new kinds of rules, which is kind of different from the clinical knowledge that people had having in the past, right? So that is one of the main motivations for why analyzing that data is an important thing, right? Of course, if you're a student or you're a recent graduate, the reason why you should really care about is industry is going after it, right? So there is industry, and obviously with the presence here, it's quite obvious that industry is interested in big data. And so there was a report from McKinsey, which quite often produces these big data reports, which basically say in the US, there will be lack of talent, analytical talent related to big data by 2018. So there is a lack of around 150 to 200K people they would need, but they are not sufficiently trained. So that is one of the motivations for this tutorial, to basically try to, I wouldn't say educate, but trying to organize the existing technologies in a more cohesive manner so people can remember some of the technologies and relate what technology has benefits and what doesn't have, and depending on the application, you can see what platforms are better and what are not. Okay, so that is one of the things. And it is also shown that the growth rate is 10% a year. It is more than the software industry. In early 2000s, software industry used to really be the hype. I mean, it used to be the real thing that industry needs. But that has changed now, that big data is the one that is being needed, right? So digital world is the future. I mean, data is only going to get bigger and bigger. Many more applications you will see. So big data is important, okay? So why do we need a platform? So that is all about big data I'm going to talk about, because the last 2-3 years back when I used to attend big data talks, I mean almost 45 minutes is going to be on big data, importance of big data and things like that. But now that's all you will see about why big data. Okay, now I think you have enough motivation or things to see. But to understand big data, first thing is to make it clear what kind of platforms or what are the things that we need to understand about the platforms, especially in the context of analytics algorithms. Before you start the algorithms, it is very important to see what kind of platforms are available for big data, right? So the reason why platforms are important is because some platforms are good for real-time applications and some platforms are good for scalable applications. So depending on the application, the choice of the platform plays a critical role more than the analytics algorithm itself in some of the applications. So to analyze voluminous and complex data or to obtain results in real time, single machine may not be sufficient, or a single machine and a commodity hardware might not be the right tool to use for the application, or maybe it might be the right tool. You don't need to really go for fancy big data platforms. So to understand better, I mean, first half of the tutorial is going to be about different kinds of platforms and what are the strengths and weaknesses of all these big data platforms. It doesn't have to do anything with analytics. It's just about the platforms itself. Because when we started this work, so that I need to give some motivation of why we started this work. So when I started looking at a big data analytics, so this started from a course that I was trying to offer, and I was looking at big data analytics. Obviously, my interest is on all the analytics algorithms. And then I thought maybe we should look at the platforms and try to see what platforms are useful. There was no real good material out there. This was almost 2-3 years back. And so we started preparing. So a couple of my students helped me in preparing the strengths and weaknesses of these platforms and implementing these analytical algorithms on these platforms and trying to analyze what are the strengths and weaknesses of these platforms. So that's how the tutorial was born. So I'm really thankful to 2 of my students who did their thesis and they graduated recently based on this topic. Right? So what we are going to look at is the different algorithms, some of the algorithms, and before that we will look at the different platforms. Okay, so that is the essence of what we will see in the algorithm. Right? When you decide on the platform, we have to first analyze at a very high abstract level what are the things that one has to look for when you have an application in hand, when you have a platform that you want to build on. There are some components that one has to very carefully think about before making the final decision, right? So we categorize that into 2 groups. One is from the application or the algorithm perspective. What are the important issues that one usually thinks about from a real practical application? And then there are these platform or system level requirements or the constraints or the things that are important for developing a good, successful application. Right? So from the algorithm perspective, the first thing is obviously how quickly do you want the results? Do you want it to be in real time? Can you wait for model building? Can you wait for evaluating the models and so on and so forth? So how quickly do you really want to build the model or want to get the results out of it, right? So then how big is the data to be processed? So are we talking about just a few megabytes of data to gigabytes or terabytes and so on, right? Then some platforms are very friendly for any kind of algorithms, and some platforms do not do that well when you have iterative algorithms. So usually most of the analytics algorithms, there are a lot of algorithms where there are a lot of iterations. So when you have a lot of iterations, some platforms might not be suitable or might not be the friendly platforms to work with. So we need to understand from the algorithm perspective, if you have the lot of iterations, then what are the best platforms that we should go after, right? So from the systems perspective, this has nothing to do with the analytics now. So the first part is about mostly algorithm and analytics component. The second one is about the platform and the system itself. So what are the things that you think about from the platform perspective itself, right? So will there be need of more data processing in the future? So in terms of systems, some systems are easily scalable, some are not, right? So in terms of the system itself, what are the things that one has to think about in terms of for a particular application in mind, and how critical is the data transfer between I/O or transfer between different hard disks to I/O and so on and so forth. Right? So the final thing is, how robust do you want the system to be? Obviously, everyone wants to have a system that is robust. When I mean by robust is when there is a system failure, when one particular component of the system is failed, how robust do you want? You still want to have the result. So how fault tolerant do you want the system to be, right? So that is one of the criteria. So if you think the application is too long and you want to definitely have a system that is robust, then there are certain platforms that are really good for this kind of applications, right? So we will look at all these issues in a more thorough manner, in a more rigorous way for this. So in terms of the tutorial itself, so we have, so first I introduced what is scaling and different kinds of scaling platforms, horizontal scaling and vertical scaling. So in horizontal scaling, peer-to-peer, Hadoop and Spark are very popular, prominent examples. And in the vertical scaling, there are these HPC, which are also called as supercomputers. And supercomputers fall into that category. Multi-core, which is the regular, almost standard desktop that you use on a daily basis. And GPUs and the FPGA, which are more hardware-oriented systems, right? So these are the platforms. And so a detailed information about these platforms is available. I will just show one slide for each platform, what it does and how it works, and then we will start with then we will talk more about how to compare these different platforms. So comparison of platforms based on the characteristics that I just mentioned in the previous slide. Based on these characteristics, how do we rate each platform? So the rating of these platforms on for different aspects that we have here, how do they rate on these platforms? So that will be the first part of the tutorial, and hopefully it will be done with it around 3:45, 1 hour 15 minutes. We'll be done with that part. And the last part will be, the second part is going to be about analytics algorithms. So in that part, we will start with one classification and one clustering algorithm and try to implement that in an efficient manner on all these platforms. So try to see the advantages and disadvantages of each of these platforms with respect to these algorithms. So I will introduce the algorithms for those of you who are not familiar with these analytics algorithms, but how these algorithms can be implemented efficiently. And these algorithms are some of the, I wouldn't say the best algorithms, but they are the ones that can explain all complexities associated with analytics algorithms that you might be using other than the algorithms that I'm going to present today. Okay, so that is how the overall tutorial is going to be structured, and we can make it more informal. I mean, you can feel free to stop me. It's just I don't have to talk all the time. If you have any concerns or questions, or if it's not clear to you, just stop, because if it's not clear to you, it's very likely that it's not clear to your neighbor as well. So just stop me in case if you think there is something that's it's not clear to you. Okay. Everyone okay with so far? So in terms of the sound and everything? Okay. So let's start with the scaling. Scaling is the most important thing, and as I said, the first part of the tutorial is coming from this journal article, which is a survey article that we published last year in 2014 about all the platforms and the characteristics that are important for a real-world application and the ratings of each platforms with these characteristics. The second paper that we just submitted, it's under review, and if you are interested, I can share it with you. It's about the different algorithms and how they are implemented in the real-world application, or in the platforms for some of the critical applications in classification and clustering. Okay, so that is how. So in terms of the scaling is the ability of the system to adapt to increasing demands in terms of processing. So basically, if I have a system, I'm happy with what's going on, but if I have more processing to be done in the future, how does it scale up? There are two ways to scale up. So this is this horizontal scaling, which involves distributing the workload into multiple machines. Usually the multiple machines are commodity hardwares, the simple system. So you have a system, you are running some algorithms on it, and you can parallelize it into multiple machines. And this is the classical example, is a peer-to-peer network or a Hadoop environment, where the system that you are going to add is not sophisticated. It's just a simple commodity hardware that you are going to add to your network of machines that are already existing. Right? So multiple instances of an operating system on different machines. So the vertical scaling is usually called a scale-up. is where the GPUs or the supercomputers are, it's a single machine, and you're trying to increase the performance by adding memory to it and adding the performance ways to improve the performance within a single machine itself. So that is about vertical scaling. So people call this as scale out and scale up, where you try to improve the performance within a single machine, or scaling out within a network of machines. You try to keep adding new components or new hardware to the existing set of machines that you already have. Right? So usually the vertical scaling is installing more processors and more memory and faster hardware, typically within a single server. So since it's a single operating system, you have more control to work with that system. Right? So there are advantages and drawbacks for each of the categories. So in terms of the horizontal scaling, here are the advantages. So as I said, this is scale out. So you keep adding commodity hardwares. There's really not much limit on the number of things that you can really add, right? So, and financially, because you're adding a simple system to the existing network, it's much cheaper to do this, right? So it increases performance in small steps. Okay. So in terms of the drawbacks, the software is not readily available, so you need to make sure that you have some kind of code that can allow for distributing the workload across multiple machines. So the software, there is some software overhead, and you don't have complete control as we have in the single machine. And you will see that very clearly when we have vertical scaling. When we have vertical scaling, the advantages being the software is easy to handle, because if we are talking about a single machine, single operating system with just more capacity in terms of processing power or the hardware or memory, right? So we don't really need to expand the operating systems or the things that we are already doing, because the capacity is just the capacities that we are increasing. Right? So it's easy to manage, install hardware. There are existing softwares that can do the parallelism. Everything is very inbuilt. So if your goal is to just make sure that it's within a single environment, you don't want to keep overloading with the parallel processing part, then the single machines or vertical scaling will be a better choice. Right? So the disadvantages being it's financially more expensive, because these are more specialized hardwares than just a commodity hardware. A commodity hardware is just like a CPU. You can add it, and Hadoop, you can, if you have 5 old machines, you can create a Hadoop very easily out of these 5 old machines. But in this case, it's a more specialized memory and the processors and so on. So this is not very cheap. And maybe in the initial stages, so plug in and plug out is not that easy. So if I have 20 machines lying out there, I can remove 5 machines and I just have 15 machines and I can run. Whereas in here, once you buy the hardware, you have to use that hardware for any application, whether you may not need it in the initial stages, but you still are wasting the resource that you have. Right? So this at a high level, what are the advantages and disadvantages of vertical scaling and horizontal scaling? Okay? So in terms of horizontal scaling, I have a couple of slides on each of this, 1 or 2 slides on each of the sliding. So these are the most popular ones are the peer-to-peer networks, Apache Hadoop and the Spark, in terms of horizontal scaling, where you have more machines that you're adding to your current system. For the vertical scaling, you have this high performance computing, the HPCs, popularly known as HPCs, where you try to scale up within a single machine. You add by adding more memories and so on. Multi-cores are the ones that we used on a day-to-day basis in usual environments. And GPUs are very fast processing tools, and these are also scale-ups. You can scale it to as much to a certain limit. You can scale that performance. Right? FPGAs are kind of old. It used to be very popular for computer vision applications. They are the hardwares where algorithm can be embedded within the hardware itself. So there are some advantages and disadvantages doing that. So we will talk about those things as well. These 4 categories are into the vertical scaling group, and the other 3 are in the horizontal scaling group. Okay. Of course, there are different variants of it. So Apache Spark, there is Storm and other things, but you can broadly classify them under these 3 categories, depending on what you see. Okay. So let's talk one by one on each of these platforms to a certain extent. I'm not going to give all the details about these platforms, because that's not the real purpose of the tutorial, but I will just introduce you enough to see to appreciate the drawbacks and advantages of each of the platforms. Okay. So let's start one by one. So peer-to-peer networks. So peer-to-peer networks, I mean, it used to be very popular in the 90s or even early 2000s. So if some of you are familiar with the Napster and Kazaa, where you can download movies or music from other machines. So it kind of sometimes it's illegal downloading or even downloading other files, large files. Basically, you are connecting through the internet to other machines. So you are working on your machine. You have this Napster or Kazaa, this software going on your system. You can transfer files to any other machine. So practically, the size of the system is unlimited. So you can have millions of nodes. Each node is a computer. So millions of nodes can be connected through the internet. Obviously, internet is slow, so there is communication is a very heavy, it's a very high cost. I mean, you cannot easily do some kind of real-time processing. This is a very bad thing to do. So the message passing interface was the way to communicate between the nodes, and so due to the slowness of internet, the actual data analytics algorithms itself are usually not used. So peer-to-peer file sharing is what people used to use this platform for. Okay, but it is still out there, and one can potentially consider that to be a horizontal scaling platform. Okay, scale is practically unlimited. There can be millions of nodes, and each node is capable of storing and processing the data. So within the data, you can. The main drawbacks, as I said, the communication is a major bottleneck. It's not easy to do some kind of analytics. You can broadcast the things that you want to do, but aggregating the results is not a easy thing to do, right? And most importantly, the fault tolerance of this system is pathetic. So there is no, if some systems fail in this network, there's no way to really do any kind of fault tolerance in those machines. So there are a lot of drawbacks, and this was one of the first horizontal scaling platforms that gained popularity, as I said, in two decades back, and so we still have it as one of the categories, but they're not very popular because of the growth of the Apache Hadoop and Spark in the recent times. So Hadoop was an environment that was started in Google in 2004 through a classical paper on the Hadoop file system. So there are really two components. It's a distributed file system. So it's a very popular technique, and some of you might be familiar with Hadoop. It is a horizontal scaling platform. So you can add machines, and it's easy to really scale out on many hundreds of machines. And it has excellent fault tolerance. So the fault tolerance is very good because it makes replicas of the data, and in terms of the fault tolerance, these are one of the best platforms. So because of that, it's very popular. So the architecture of the Hadoop has these two main components: the distributed file system and the Hadoop yarn, which is the resource management layer. Right. So if you look at the architecture of Hadoop, so you have the distributed file system as the base, the layer, and then you have the Hadoop yarn, which is the management layer, resource management, try to see where to do what. Right. That is the main purpose of the management layer. So what kind of tasks should be done on what machines, and so on. Then you have this Hadoop MapReduce. So we'll talk about MapReduce in a few times now, and in the second part of the tutorial, I will explain how to do an algorithm in MapReduce environment. So let's just postpone that for a few minutes. And then there are these wrapper programs, Hive, Pig, and so they make the job easier in terms of implementation. They are kind of scripting languages, so they make the MapReduce tasks, everything much easier for you. Database, HBase is a database. Storm is for real-time applications, making things in real time, and so on, right? So that is the basic data processing architecture in Hadoop. So the main programming form is about using MapReduce. MapReduce is a very practical way to solve a parallelization problem, where you have mappers where if you have a task that is parallelizable, that is one condition that we need to see before we start with Hadoop. If there is a task that is parallelizable, and so there are these two ways this MapReduce works. Once you do different mappers, do tasks individually in a local system, and the reducers aggregate the results from these individual tasks and give you the final result. So this will be more clear to you when we talk about the k-means algorithm, or how the mapping is done, how the reducing is done. All these things will be more clear to you in the second part of the thing. But at a high level, this basically follows a divide and conquer strategy, wherein we try to give the entire workload we try to divide it into multiple workers, and each worker produces its own local result, what we call as a local result. And these results are aggregated, and finally the accumulation of the results is being output as the final result at the end of the reducer step. Okay? So this, in the broad manner, you can consider this to be a partition. The first part is the partition, and the second part is about combining the results. Okay, so this is, at this point, I think this is enough to know about MapReduce. But as we move on, we will see more concrete examples of how mapping is done in a analytics algorithm, analytics environment, in an easier manner. Okay, so as I said, the wrappers, they help in coding. You don't have to code each and every step, the mapping and reducing. There are ways to, the scripting languages allow you to do things more automatically. And this was developed in many of the Bay Area companies use these wrappers for doing these tasks. Okay. So Spark is a very recent technology developed at the University of California, Berkeley. One of the main drawbacks of Hadoop, where you try to, after map and reduce step, you try to put the results in the hard disk, and if it's an iterative algorithm, it's very inefficient. The Hadoop environment is very inefficient because you keep writing into hard disk and then reading back from the hard disk, which makes things very slow. So based on that motivation, instead of writing to the disk, Spark writes it into the memory after the result step. So in this picture, after the result step, over here, it writes back to Hadoop environment, writes back to the disk, and once again you can read it from the disk and do the processing. This is what is done in an iterative algorithm. And but for using Spark, you do everything within memory. So it's very, very fast. You will see in some of the iterative algorithms, Spark works. I will show you towards the end again. I will show you in terms of an iterative algorithm, Spark will be much faster in terms of, and in some cases people have shown that it is almost 100 times faster for some of the basic data mining or data analytics algorithms. By using Spark, you can make it tens or hundreds of times faster. Okay. And it supports Java and Scala. One of the drawbacks is that it is new, so there are not many wrappers or many things that are done as much as people have done on Hadoop. But it is very fast-growing environment for people to consider. Okay. Again, Spark is a horizontal scaling platform. You add the machines. The main difference being that instead of writing to the disk, you are going to write into the memory. Okay. So that is one of the main differences. Okay. So that is about the horizontal scaling platforms. And the vertical scaling platforms, these are the 4 vertical scaling platforms. The HPCs, these are the most popular way to look at it is the supercomputers, right? So these are single machines where you can add blades and you can improve the process. And the hardware is a very specialized hardware. They are very extremely highly fault tolerant. So there's no way that the hardware is going to fail. So these are very powerful machines. And there is a limit to how much you can add to a single HPC, but it is much bigger than any other vertical scaling platforms, right? So in terms of the scale up, but one drawback is that it is very expensive. It's not very easy. So it's not easy for an academic professor or a small company to buy HPCs as much as we want. These are expensive devices or systems. Okay, and they're not as scalable as Hadoop and Spark. They still have certain advantages. We'll talk about it a little bit later. Okay, so that is one of the things. So the multi-core CPU is the one that most of us are familiar with. I mean, if you are just using a computer, usually there are quad-core machines, and these days the machines are becoming 16-core, 32-core is becoming very commonly used for doing processing. Again, each core is independent of each other, so you can do things in different cores. The parallelization can be done within cores. I will show you the architecture of a CPU as well as a GPU little in a while. So the main parallelism you can do is multi-threading, right? So you can take a task, you can decompose the task if it is parallelizable. Again, most of the things you can take advantage if the algorithm itself is parallelizable. There are some serial algorithms that no matter what, you cannot take the advantage or benefit of a parallel environment, right? So things if you think, and I will show you a trick where most of the analytics algorithms you can definitely parallelize. It will be very hard for you to show an analytical algorithm where you cannot parallelize. The extent to which you parallelize is debatable, but there is always some component where you will parallelize. I will show you a list of plenty of algorithms at the end where most of these analytical algorithms, there will be at least some component where you will be able to parallelize. That is one of the take-home messages for this course. Just, I mean, even though at a high level, when you look at the algorithm, it is serial. Some of the algorithms look serial, but still there are many ways to parallelize even a serial algorithm. So that is one of the things that take-home messages that I really want to get. But that let's get to towards the end of the lecture. Okay. So newer broods of motherboards are coming. It's a upcoming area. So people, 10 years back, there was no concept of quad core machines, but now quad core machines are very common, right? So now even 16 core machines, when we buy, we look at 8 core, especially if you are doing some heavy duty processing. When we buy, there is no use of buying a single core or a dual core machines. If you are serious about processing, we look for 8 core or 16 core, which is very cheaply available, by the way, these days. Okay. So that is one thing. So the tasks is broken into thread, and we do the multi-threading for parallelizing the tasks. Okay. So the GPUs, they have rich history because they originally started from the gaming industry or from more specialized applications, but then they became more mainstream. These days, people are talking, especially if you're talking about big data and trying to get results in a real-time manner. GPUs have gained a lot of popularity. GPUs are one of the best tools to consider when you have limited amount of data, not really petabytes of data, but when you have limited amount of data and you want the results to be very, very fast. You really can't, it's a real-time application. So GPUs have gained a lot of publicity in the recent times. Right? So there is a general purpose GPUs in this. We are no longer using just GPUs just for the gaming industry or one particular application. So they became into mainstream. Any kind of application can take advantages of this general purpose GPU, the graphics processing unit. The main reason why GPUs do very well is because as opposed to a DDR3, which is a system memory that is used in a multi-core or any standard machines, GPUs use a more advanced memory, which is much, much faster. It's called a DDR5. So if you are interested to learn more about GPUs and what this memory does, you can just type in DDR5 and DDR3, and you can understand the differences. Because of this specialized memory, GPU produces the data transfer, the I/O transfer within GPUs makes it much, much faster, as opposed to just a system. Memory itself is faster than hard disk to memory transfer. Doing things within memory is much faster, but a DDR5 memory makes GPUs even much faster, much more faster. Okay, so NVIDIA is the one that uses this, and they developed this CUDA environment, and it's very popular environment. And the programming is not easy, but it is still possible. So there is the overhead of my students always used to complain, GPUs are not easy to program, but this CUDA programming language makes it much easier. It's not a wrapper, it's not a scripting language. It provides a platform where initially, before the CUDA language came to popularity, the writing a GPU code is much harder because you need to deal directly with the hardware components within your code. That kind of dealing with the hardware directly is abstracted using the GPU. So now it's gaining a lot of popularity, and with applications in Bay Area using deep learning and these more real-time applications, GPUs are being used very heavily for mainstream applications these days. Okay, so that is about the CUDA programming, and so you don't really need to do so the GPU architecture has multiple multiprocessors. Each multiprocessor will have certain cores. These cores over here should not be confused with the same kind of cores that you have in a multi-core machine. Multi-core machine usually core is very powerful as opposed to a core within a GPU. So now you can see a couple of thousand cores within a GPU, and is very readily available. A cheap GPU these days, you will get 2,500 cores. And each core is lying within a multiprocessor. So you have certain, the GPU architecture, you have certain multiprocessors, and within multiprocessor you have number of cores. So this will be a typical architecture. Because of this particular nature, parallelization becomes much, much easier, right? But one drawback of this GPU environment is that you can parallelize the code, but each core is not very powerful. So when you parallelize the task that you are going to parallelize, if it is a very compute intensive task, then a standard core will do much better. Whereas a processor, the core within a multiprocessor, there are a lot of them. So as opposed to having 4, now I have 2,000 cores within a multiprocessors, right? So if you really have a task where you want to parallelize, it's easy to parallelize, but each parallel task is not very compute intensive. GPUs are the best platforms to do that. And of course, when you have a limited set of amount of data, maybe several hundreds of gigabytes or just then GPU can handle that. So this is the context where GPU can really be very beneficial. Okay, so the core over here, the power of a core over here is very, very small compared to the power that a core can do. So within a task, I will show you later an algorithm where tasks can be parallelized, and within that parallelization, some tasks are very compute intensive, in which these cores are better. And remember that this is within the GPU architecture itself. Usually when you have a CPU, you can install this GPU as an add-on, and you can have the CPU on top of this GPU, and I will show you the final architecture where within a GPU, within a machine, you have the CPU, its CPU memory, and then the GPU memory and the GPU hardware over here. Right? So everything will be in a single system, and you can keep adding the GPU machines as much as the machine allows you to do. Okay? So that is the key difference between the cores within a CPU and within a GPU. Okay? So the CPU and GPU, the processing power of current generation CPU is close to 10 gigaflops, but the processing power of GPU is close to 1,000 of gigaflops because of the parallelization and multiprocessor. As I said, there will be 2,500 cores. That's a very common GPU. The Tesla GPU hardware, you can plug in this. If the CPU has a slot for advancing it to GPU, you can plug in a GPU, the plate of the GPU into the slot. Okay. So CPU primarily relies on system memory, which is slow, but GPU has the memory is much faster. The GPU, one of the problems is the software. So the software, the applications that take advantage of GPU are rather limited. So you will have to end up doing a lot of coding by yourself. So that is one of the drawbacks. Though things are changing very rapidly in the last few years. Okay. So CPU has been around for many years. So the coding, a huge number of softwares are available. Okay. FPGA is a very interesting device. So it looks something like this, and when you have real-time image, the computer vision or image tracking applications, you can. So let's say you have an object detection algorithm, and you really want that to be in real time. If you have a car, you try to have a camera to the car, and you want to detect it very fast, right? You really need a real-time scenario. Here, this is a real-time scenario where you are on a TV, and even in medical applications, you want to track the valve of a heart or any CT scans. You are trying to track some of these images. You really need the algorithm to be extremely fast. So the FPGAs allow you to do that by embedding the algorithm directly onto the hardware. So you can directly code the algorithm within the hardware device using this particular technology. You can directly code the algorithm within the hardware device, and you can use that for real-time applications. They used to be very, very popular, but then changing any component in the algorithm is not easy. So because it's directly related to hardware, if changing the algorithm even little bit is going to be very, very expensive, and it's pretty much you have to throw it and redo it again on the hard drive. So it's very, very complex in terms of software development or any changes to the algorithm. Because of that, they are gaining popularity again. Intel is trying to push for it again, but 2 decades back, when you had the growth of these imaging applications, image tracking applications, or the real-time computer vision applications, they used to be very, very popular. You can do biometric. As long as you know this is the algorithm, this is the final algorithm you want to do, you're not going to change it anymore. This is the fastest platform that you can get, because this is as close as you can get to the hardware, and it usually even beats the GPUs in many cases. Okay, so this is again, all these are coming into this category of the vertical scaling. This is not about new machines, adding machines to your current system. It's within a machine, adding more slots. Within that slots, you either in terms of blades or in terms of GPUs, in terms of cores, or in terms of this additional hardware like FPGA. Okay. So this is where we are at, and any questions until now about the platforms, because the next part of it is going to be about the actual characteristics, what we are looking for from the analytics point of view. Before even we know about analytics, from the analytics point of view, what do we really care about? What matters from the analytics point of view? Any questions or any comments you want to share? Is it okay, or is it too boring? Any feedback you want to give until now? Okay, yes. Yeah. You're okay? Yeah. So you had a question. Yeah.
Just quickly, I noticed you didn't mention solid state flash memory in this
So usually when we looked at the analytics platforms, we haven't looked at, I mean, there were not many analytics kind of platforms where you have, so when you say computer vision applications, at least there is something in analytics. When we say solid state thing, we haven't looked at, we didn't have any papers that are available on analytics for flash memory, or that was an interesting point, but at least in the literature we haven't seen anything so far, so we didn't include that part in. Okay. There was also, last time when I gave a tutorial, there was a question about what happens if you want to do it in a cell phone or a cell environment where you have limited. But usually the analytics in when you have within a cell phone where you have limited memory, limited, everything is limited, most of the analytics is done in the cloud. So once you send it to the cloud, these are the platforms that you can use in the cloud. So the analytics, anything that is very serious about analytics, usually they are not done, even I assume that it's not done in a flash memory, even within a cell phone. Analytics part, which is little intensive than just simple processing, is usually the data is sent to the cloud, all the processing, analytics, everything is done in the cloud, and the results are sent back. Because a cell phone doesn't have the potential, not the recent ones, but usually most of the analytics and processing things are not done within a cell phone or any mobile devices. So probably even for the flash drive, usually most of the processing things are done in the cloud. These are the things that I will show you in the Amazon cloud. We can implement most of these platforms. So I can show you later and things. Yes.
If Hadoop was relying more on main memory for processing,
yeah,
and future updates, would it also perform as good as Spark? Or
yeah, actually, Spark is nothing but doing that. So Spark, the main variation of Spark and Hadoop, the question is, if the Hadoop had done things instead of putting on the hard disk, if it does in memory, then that is pretty much Spark actually. So that's how Spark evolved. But there are advantages. So though, it becomes slow, writing to hard disk has certain advantages. Just overwriting the memory, you don't get the updates in a regular basis, right? So when you have iterative algorithms, you want to monitor how the iterations are progressing. Writing into a disk is not such a bad thing, unless you are looking for a real-time application, in which case you can go for GPU anyway. So Spark does have a lot of advantages, but writing into a disk, I'm not too much against that, because in the iteration results, because usually when we are trying to manipulate the algorithms, we try to see how the iterations have performed over a period of time. In Spark, when you write it in memory, when you are overwriting things, you don't have a storage of that, you don't have a log of what you have seen, it may not be such a great thing for iterative methods. But that is just my point of view. Usually when people talk about Spark, they always talk about advantages. But when you really do it in practice, and especially in my applications, we are not really real-time people. I mean, in industry, maybe you really care about in real-time, but many applications, we can afford to wait in many of the things that we work personally on. In healthcare, I mean, yeah, doctors give the data, but then you need to make decisions in real time, but model building doesn't have to be in real time. You can do it offline. In many cases, model building can be done in offline, where the most analytics algorithms have to be made more efficient in the model building stage. Many algorithms are good for getting real-time decisions. When you give the features, new features you get, the algorithms are good enough to do in the testing phase, in the real deployment phase. Right? But that is just my point of view.
I've also
Okay, yes.
heard of a term called Storm.
Yeah. Storm is for real-time streaming applications. It is done on Apache Spark, but mostly for real-time streaming applications. So it's kind of a wrapper. So that is one of the things that I already had over here. But it is really meant for dealing with real-time applications. How it does, this is a wrapper that is on top of Spark, which can handle the real-time part in a more efficient manner. So when you have the updates, and so the real time, so there are the streaming tasks that you can abstract some of the streaming applications, right? So streaming, how to store streaming data, or how to summarize streaming data, and so on. For that, Storm is very good. Okay.
So does it sit on top of?
That is my understanding of from what I read. Okay, but and definitely this is not a separate platform to consider. This is only for making things work better in a real time by adding wrappers, by abstracting the streaming applications. So for streaming application, if you take two streaming applications, you can always abstract the functionalities that are common to both streaming applications. So that functionalities of what you can make it common to all streaming applications is what Storm provides. Okay, so that's the main thing. Yes. So I think with respect to time, I think we are a little behind than what I initially planned. So let's. Okay. So in terms of, so this is where we are at about the platforms, the basic description of some of the platforms, and now comparison of platforms. So this was the thing that which really motivated us to really get into this, because there is not really a good comparison from the analytics point of view for which platforms do well, which platforms do we prefer. So this is an attempt to give some guidelines about what things matter or what things are important, what things should be considered important in any analytics or in any practical scenario when you are having an algorithm and you have a platform. What are the things that are important? As I mentioned before, from the systems point of view, scalability, how scalable is the system, data I/O performance, and how fault tolerant is the system are the important things. I will give you more details about each of the definitions and what are the strengths and weaknesses of each platform with respect to that particular characteristics. Okay, and in terms of the applications, whether you need real-time requirement or how much data do you have in the applications. Are you talking about petabytes of data? Or are you talking about just megabytes or few gigabytes of data? And whether your algorithm will have iterative, because then things change a little bit when you have iterative nature in the algorithm. So I will show you a comparison table in the next slide. And just to let you know, in the comparisons, we gave the ratings. 5-star is the best platform for this particular characteristic. The 1-star is the worst possible platform for this characteristic. And one thing I need to note here is, if I have a 3-star and 2-star and 1-star, it doesn't mean 2-star is 3-star is twice better compared to 1-star, compared to the 2-star to 1-star. Okay, so the rating is just a qualitative measure. It's not, you shouldn't literally take it as this is twice better or thrice better. So that quantitative measure is not there, and it's very difficult to get because this will become very application dependent and algorithm dependent. What we try to do is make a abstraction of what are the things that are positive for some platforms and what are the things that are negative for each platform. So you will see that the first 3 platforms over here, the peer-to-peer and MapReduce, which is the Hadoop and Spark, the first 3 are the horizontal scaling platforms, and the last 4, the next 4 are the vertical scaling platforms, HPC clusters, multi-core, GPUs and FPGA. And then there are these 6 characteristics. 3 are system dependent or platform dependent, and 3 are the algorithm dependent or the application dependent. Okay, so we will summarize what these methods are, and you will see that you can clearly see there are certain patterns that emerge just based on a single snapshot, and all the details of each of the platforms is available in this survey article which we published a couple of years back. So you will see that some of the things like scalability, horizontal scaling platforms are really good, right? Whereas vertical scaling platforms have some issue with scalability, right? So when you have the scale, the precise definition of each of these terms, I will give it in the next few slides. So I have one slide on each of this and why we are rating. We are giving justification for why something is having a 5-star or why something is having a 3-star and so on. And the data I/O performance, you will see the peer-to-peer where you have internet communication, you have poor, but apart from that you have other things, especially vertical scaling data I/O is really good. So in general you will see that vertical scaling, all of them have some advantages over horizontal scaling platforms, and within vertical scaling platforms itself, some platforms are better than others and so on, right? So fault tolerant mechanism, how robust how robust we want the system to be for hardware failures is the fault tolerance. Real-time processing from the application point of view, how much you need the real-time processing. You will see that, as I mentioned, FPGA and GPU are the best for real-time processing, whereas the horizontal scaling platforms are really not that good for real-time applications. And for data size support, again, the horizontal scaling platforms are much better. Whereas vertical scaling platform, the data size you really need to, and iterative algorithm. So I have one slide about each of them. So I will cover and why you will see from each slide and why one platform is being rated higher than the other platform. By the way, we have now no funding from any of these platform manufacturers or anything. So this is a very it is as comprehensive as what we feel as genuine as it gets. Okay, so there's nothing that I'm not promoting any platform here, or I'm not asking you to keep working on one particular platform. It's very unbiased. thing, right? Okay. So in terms of scalability, ability of system to grow the amount of work. So basically, if the amount of work increases, can the system be scalable? So, and obviously the horizontal scaling platforms will do much better because it's easy to add machines to the existing system that you have. Whereas vertical scaling machines, it's not that easy to be scalable. And FPGA do the worst in this category because once the system is there, you forget about scalability. You can't even change the machines, change the algorithm to any extent. Okay, so that is why FPGA is rated low. And HPCs have ability to scale up little better because the capacity of the HPC to incorporate new blades is much more than capacity of a multi-core to incorporate new cores or new GPUs. Okay, so because of that reason, GPUs and multi-core are not that great for making the system more scalable. So to address more processing in the future, whereas FPGA is the worst and HPC is the best within the vertical scaling category. Okay, whereas if you go for horizontal scaling category, most of them do well because you are just adding machines. So if you want more power, more processing capacity, it's easy to just keep adding machines. Okay, so that is about the scalability. Okay, so the data I/O performance. So the data I/O is about the data transfer. So it can be within a machine, within the memory to hard disk, or within multiple hard disks through the network and so on, right? So the rate at which the data is transferred. This is more precise definition for the data I/O performance. How we are trying to rank. How do we rate these platforms with respect to the data I/O performance, right? So in the context of the data analytics, you have can be viewed as rate at which the data is read and written to the memory or disk, or the data transfer between the nodes within in a cluster, right? So obviously in this case, the horizontal scaling platform, because of the multiple nodes and multiple machines, horizontal scaling platforms don't do well. And if the communication is like in peer-to-peer, if the communication is between different machines through the internet, then the I/O transfer is pathetic, right? Is the worst. And Hadoop is good because you have the node cluster within the cluster. It is better than a peer-to-peer network, but still, because of the I/O overhead when you're writing to the disk and reading from the disk, Hadoop is not rated highly compared to a virtual cluster with the Spark clusters, right? So uses system memory, minimizes disk access. Because of this advantage, the Spark will have better performance in terms of the I/O, data I/O transfer. And HPC and multi-core use system memory. And so these two, because the system memory is the standard memory that we use in our daily machines, the system memory usually within a single machine. So these are faster than the horizontal scaling platforms, but they are much worse than this FPGA or GPU, which uses more specialized memory, which is the DDR5 memory that I mentioned. Because of that, the I/O transfer between the of the data becomes much faster in the context of GPUs or FPGA. So this is about the data I/O performance. So fault tolerance, how robust is it for hardware failure? So if the system fails, if a particular system fails, will the work can the work still be done, right? So peer-to-peer is the worst in this category because if once the system fails, the processing stops and you don't have any control over that machine, right? Anything over that. The reason why we give 4 stars for the, so let me explain first in the horizontal scaling category, the Spark and Hadoop has inbuilt fault tolerance mechanism. So the first version of Hadoop, which was released in 2008, when we started the Hadoop work in 2010, the first version of Hadoop I really didn't like because we don't have control over the resource management. Hadoop does its fault tolerance mechanism by itself. Bottom line is Hadoop and Spark are extremely good for fault tolerance. They have inbuilt fault tolerance mechanism. You don't have to do any coding or anything for doing fault tolerance, and the system itself will take care of it by giving replicas into different machines and making sure the data is not lost or any processing results are not lost. The first version of Hadoop, when it was released in 2008, we didn't have, as a user, I didn't have any control to look at what system, what nodes can I go and do the processing. So some nodes, even if the work is done, they sit idle, right? Whereas in the later versions, in 2012, the Hadoop released second version, and then the third version, I don't even know recently what is the recent version, but as we get newer versions, the user has more control for the fault tolerance as well. So by default, Hadoop does some kind of fault tolerance, and if you're not happy, you can change the fault tolerance mechanism in terms of how many replicas you want to make, how often do you want to make the replicas, and so on and so forth. right? So built-in efficiency of built-in codes are extremely well done for the Hadoop and Spark environment. So because of that, you get we give the 5 stars over here. Whereas most of these other platforms over here, because we are talking about a single machine in vertical scaling platform, these are specialized hardware. It's unlikely it becomes fault the hardware failures. It's very unlikely that the machine breaks down when you are having a GPU or so. The fault tolerance is not a big issue usually when we talk about vertical scaling platforms. But you still, if you have to worry about it, they don't have any inbuilt fault tolerance mechanism. We are just relying on the fact that the hardware doesn't break that easily, as opposed to a cluster of nodes where a node can break very easily. Here, since we are the ones who got all the hardware and everything is in place, the likelihood that a inbuilt hardware fails is very, very low. Because of that, because of the fact that it's very robust, it doesn't fail that often, we give 4 star, but not 5 star, because we have to add additional coding if you are still interested in for making it fault tolerant. Okay. That's about fault tolerance. So until this, it's about the system side. Now it's about the real-time processing is about the application side. So as I mentioned, for the real-time processing, usually the vertical scaling platforms are much better, and FPGA and GPUs do the best because of the thousands of cores, because of 2 reasons. Thousands of cores that are available in GPUs, it's a very strong component, because the parallelization becomes much easier. So if you have a task that is parallelizable, because you have 2000 cores, you can easily parallelize things. You can make things much, much faster. There's no other platform that has that many cores in parallel unless you have Hadoop with 2000 machines, right? In which case the communication is still a problem, because you're talking about communication between different nodes. Whereas over here, we have a single GPU where we have all the processors within, so it's easy to just transfer memory from the GPU memory to the CPU memory. It's much faster. Okay, and very high speed because of the DDR5 memory, and these two use the specialized memory, and the fact that they have thousands of cores makes for real-time applications. These two are the best platforms compared to any other platform. Whereas the HPC and multi-core still are better than horizontal scaling platforms, because in the vertical scaling you still are talking about a single machine. May not be the super memory. It's not the DDR5 very fast memory. At least it's a system memory. You're dealing with a single machine and the memory, so it's still faster. Whereas peer-to-peer is again very slow because of the slowness of internet, right? So you are talking about transferring files and everything through the internet. Whereas virtual, the Hadoop and Spark, they are slow in terms of data I/O and the optimized powerful hardware. Okay. Data size supported. Again, this is exactly opposite for what you have seen, because over here you will see horizontal scaling platforms are bad because of the real-time capability is not great. Whereas over here, because of the trade-off between the data size that can be supported, within vertical scaling platforms, there is always a limit at which, I will show you in the experiments, you cannot go beyond certain data size when you have these vertical scaling platforms, because you are talking about a single machine, and there is always an upper bound, upper limit of how much processing it can do, how much it can really process. Whereas over in the horizontal scaling platforms, you will see that they are usually much, much better. So the reason why peer-to-peer gets a little better than Hadoop or Spark is because potentially there can be millions of nodes. You can run petabytes of data because there is no limit to the number of nodes, whereas a Hadoop cluster or a Spark cluster of machines usually has still limited number of machines. So they can handle terabytes of data, but for petabytes, it's not very usual to have petabytes of data within the Hadoop environment and so on. Right? And HPC clusters also can, depending on what cluster you're talking about, some of the supercomputers, the best machines out there within HPC can also handle as good as several terabytes of data very easily. But usual HPC clusters are not that much capable. And then the other vertical scaling platforms, multi-core GPUs, they are not suitable for large-scale data sets because most of it is about the power of memory, and it relies on system memory, and which can only be up to hundreds of gigabytes and limited onboard memory. Okay. So the last one, it may not be very generic, but the iterative task support is an important thing for analytics applications, analytics-based applications. So when it's iterations, then Hadoop is inferior to Spark, that as I just mentioned, because of the writing to the hard disk. But when you have iterative tasks, usually vertical scaling platforms do much better, because we are talking about writing everything to within the system memory itself, or the memory within the machine, as opposed to writing it to the disk and even the memory with a cluster of machines, right? Like what Spark does. Okay, so the ability of the system to efficiently support iterative tasks is the iterative task support. Okay, so this is the summary, and let's take a small break, just in case if you are getting bored, and you can ask any questions. And if you want to have a small break, 5-10 minutes, then you can take a break, so that I don't want to just bombard you with information. So it just maybe you can check your emails or yeah, yes. I can't hear you, sorry.
So with the internet getting faster for things like rock fiber and things,
Yeah, sure.
do you anticipate a virtual customer as far as data performance like that?
Yeah, see, but this rating is biased towards the analytics algorithms. With respect to the analytics algorithms, it's still not, it cannot be. But in terms of file sharing and data management, database, other issues, peer-to-peer can do as good as Hadoop for some applications. But when you talk about algorithms, because the drawback of peer-to-peer is not just about the slowness, but also when you try to aggregate the results, you need to know which task you are given to which machine. And you don't have control in a peer-to-peer environment. So in analytics, when you want to parallelize and you want to aggregate the results, it's not easy in a peer-to-peer environment compared to a Hadoop environment. Yeah, so for analytics, it's not easy.
So let me ask you a question. If it's like environmental kind of the weather, temperature, having the optical physics modeling, to have the resolution, and would it have more predict to the study of the Earth and to the 10 kilometers versus 10, 100,
Yes.
that gotta be vertical, right?
Yeah, but then it depends on what kind of processing you're doing. So when you decide on the vertical or horizontal, so what do you do? I mean, what kind of analytics or what kind of processing do you do? So what kind of model is that?
The weather, predict.
Yeah, but predict, but what is the underlying algorithm? How the algorithm is structured?
Well, the underlying data would be the temperature, the
Yeah, but
pressure, the physics part of the machine, right?
Okay.
So maybe I have 510 input to it, and the humidity, the air pressure, these things, right?
Yeah, sure.
Temperature,
Okay.
velocity,
But then,
like 5 things to feed to it at different locations.
Yeah. So,
And if I want to have a very, very high resolution to, like just imaging, right? Did they answer your question?
Yeah, I understand, but that is from the platform perspective, right? So I can see how much data you have, but from the algorithm, when you do the prediction, how is the algorithm structured?
The algorithm is
do you really need things in real time?
not right now,
Yeah,
because they don't even get it.
So that depending on that, the platforms become. Some platforms are good for things. I mean, these are the 6 characteristics that usually are kind of abstracted for most of the applications. So it's hard to say just based on the description. Maybe.
So we have to show the math of which model.
So
to decide, right?
Yeah, about the data and the platforms.
And the kind of math equation it's trying to solve, right? And do you have what kind of math equation is good for that? Because that's good to the meat of it.
So, I mean, math equations, I'm not sure, but at least from the analytics point of view.
Model part.
The model part, we have 2 models that I'm going to talk about, how to parallelize, how to implement in these platforms. And then maybe after the presentation you can
Different things
skip.
have different models,
Yeah,
right?
So that's again, we try to get the most representative of the class of analytics methods, and we implemented that algorithm. So where you have iterative component, parallel component, and compute intensive component. All the components, if they are within a single algorithm, we use that algorithm to implement and show the benefits and drawbacks of each of the platforms.
Okay.
So maybe after that part,
Okay, thank you.
Hi. Could you comment, either during your presentation or otherwise, like for instance, if you look at programming tools, the level of abstraction that is available with these platforms. Because, you know, I mean, gate arrays, where essentially it's going to be the lowest level of code. So today when we build applications, you know, we use SQL servers or web servers or whatever. So there's a certain level of abstraction available to program these things. And there are tools available of various kinds to do that. So across these platforms, could you comment on that?
Yeah, so basically Spark is a new platform, so the number of tools available are kind of low, right? Peer-to-peer, though the concept is good, for analytics point of view, peer-to-peer is a very poor thing because in most of the analytics, whenever you do parallelization, you try to send it out to machines and you need to aggregate the machines, results of the machine. So this in peer-to-peer, there's no question. Hadoop is, if you really want to pick two things where you are really concerned about the coding part, where you have in terms of the vertical scaling, multi-core codes are much more than, but GPUs are upcoming. So multi-core and GPU are the best in the vertical scaling. Hadoop is by far the best in horizontal scaling.
But the level of abstraction, the tools
yeah. What I'm saying is, of all the platforms, the best in horizontal scaling will be Hadoop.
Okay.
So
and
others
it has
are
a
poor.
level of abstraction to write
It depends on the applications you're talking about. So some cases you do have a lot of abstraction. The Hadoop, the layer that I mentioned, where you have Storm, if you have streaming applications, there are a lot of things that people do. I mean, it does a lot of good abstraction. For database operations, you have this Hive and you have HBase, so we have good abstraction. It depends on the kind of operation, but some of the standard applications and standard operations, a lot of abstraction is there. But if it's a brand new application which people have not considered before, obviously there's no wrapper.
But like for instance, for database access, and
Yeah,
so
yeah,
there
yeah,
is a
sure.
level of abstraction.
Oh, the standard operations, yeah, sure, yeah, very good. Yeah.
A couple of basic questions. What's the definition that for platform, and what's horizontal and vertical scaling? I'm just trying to get the basic.
Okay, so the platform is the system on which you try to run your algorithms. This is the platform. A CPU is a platform, right? And if you have multiple CPUs, you can connect them and you can make the platform better. So that is the Hadoop environment. So this is a platform or the system on which you are trying to run these machines.
And the scaling, how much data you can...
Yeah, so scaling is where if you have a single machine, and it has like, for a laptop, you have machine slots in which you can add more cores to it.
Right.
That is scaling up. You have a single machine, you're improving the performance by adding more components to the single machine.
Right.
Either these components can be blades in supercomputer, or it can be cores or GPUs in GPUs. So you have these GPU slots. A machine can have 2 GPU slots. You can add GPU cards into it and you can improve the performance. As long as you're dealing with a single machine and you're improving the performance by embedding things in the slots that are available, then that is scaling up. That is vertical scaling. Your initial machine, you're trying to improve the performance vertically within a single machine.
What's horizontal?
Horizontal is like if you have a Hadoop environment, you have a laptop like this, and I want to run a very big one that cannot fit in a laptop, I connect to 20 different laptops in the room. I make that as a cluster of machines. So I have my old lab had 5 old machines. So instead of just running on a single machine, if I can do the parallelization and run parallelly on 5 different machines that are interconnected within an intranet, that is horizontal scaling, adding more machines. Rather than just improving the performance vertically, you are adding more machines and making the cluster of machines work better.
Thank you.
So that's,
Being said that you want this whole availability of Spark because it's going to be being said that the real-time processing is not getting boosted in Spark. That's what I see with the ratings for the president.
Plan to stay a little bit longer. Maybe tomorrow morning.
hardware is the same. Right? Hardware is the same. So that part where you're, instead of writing to the disk and writing to the memory, is an iterative task job than the real-time process. See, there are real-time applications where there is no iteration. You just run it once. When you are running the algorithm once, Hadoop and Spark are the same. So when you are doing mapping and reducing, or you do it in Spark, the Hadoop is slow because it just writes in the disk. But that writing to the disk becomes because of the iterative job rather than the real-time processing. The processing power remains the same. It's just when you have iterations, Hadoop writes it to the disk. So the iterative task Hadoop is bad. I hope that is what. Yeah, in the iterative task Hadoop does bad. So this star over here, right? But a real-time job is about the platform itself. So this is specific to the algorithm. If it's an iterative algorithm, then Hadoop does bad compared to Spark. But if the platform itself has equal support for real-time, as long as it's not iterative.
Only if it's iterative, then writing and we are discussing.
Yeah, make the difference, right? If it's just a processing job, you do things similar in Hadoop and Spark is not much different.
And one more. The algorithm.
So yeah, as of right now, I'm a computational
Also
master.
very regarding it later.
No. See, algorithm is related to the application that you are developing.
What I'm
So,
I'm getting a little bit new to this kind of thing.
is there
As of right now, I'm doing
difference? I
Java.
mean, if I'm working with algorithm and if I'm going to change platform something.
As far as that goes, like what other
Should I see for the
platforms
impact?
are machine learning?
yeah, see, each platform is its own way of coding the algorithm. But GPU code is different from a Hadoop code or a multi-core processing. I will talk a little bit about it, but then if you have the algorithm, you don't want to change the platform. Changing algorithm is easier than changing platform. Yeah, because first of all, you need to buy the hardware. And even if you do, some platforms you have to completely code it again. So it's not easy to just change the platform because it's not interchangeable because of the hardware details that you need to do.
So they are different in some stages.
Yeah, so a lot of specifics.
Thank you so much.
Hi, Chandan.
Hi, I'm Bill Janetta with IBM. So Archipelago works for me. Do you know her? So you're here at United States, correct?
Okay.
Yeah, so Art works for me. He's a sales rep and you can't talk about your leads. He's on vacation, so he told me to come by and just introduce myself. And I'm with Anthony and we work together. But a good job thus far, but I just wanted to say hi or good job. I unfortunately have to go catch a flight because I have to present tomorrow in Minneapolis. But Art had just asked me, but you haven't met Art yet. Okay. He's new on the account. So, are you part of the med school or part of the
Computer science. Yeah, College of Engineering.
Oh, wonderful. Well, I appreciate it. So keep talking about all this good stuff. So I manage the analytics here for the Great Lakes. So for IBM, so you know, either Spark and other things that you talked about. Somebody's going to be speaking at 5:30 today. You're between us.
Yeah.
But anyway, I just wanted to say introduce myself, but thank you.
Help train and do that, and then you actually guide you. I'm sorry.
So we can start, I believe, right? I think, was it 5 minutes, 10 minutes? Was it okay? Yeah, because I mean, I don't want to. Okay. So we can start. Okay. 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 Turn off the lights. Or? Okay. Will it be better to turn off the lights or? It's okay. Okay. Okay, especially for the, yeah. Okay. Okay, so any questions on the first part? Any things? So now, yes.
When you were talking about, I think it's the second one down, Hadoop and your pluses and minuses.
Yeah.
If you stored the data out on the same unit that you're doing the processing, you don't have that much of an input-output issue to the analysis, do you?
Yeah, yeah. So that is because of the disk to memory access.
Right.
So disk to memory is slow. Because of that is the issue. Other than that, there is no real big drawback with Hadoop. Right? Just because you are writing to the disk, and when the iterations go, more and more iterations are needed, you keep reading to the disk and writing to the disk again and again.
Yeah, but if you had the whole data set broken up into some rational subunits,
Yeah.
and you also had your software distributed among
Yeah.
microprocessors on each worker, which was where the data was stored,
Yeah.
that would seem like would be fairly
Yeah,
fast
so
process.
that is splitting the data. So we will talk about that a little bit here. But after each iteration, you are supposed to write something to the disk, and for the next iteration that you are going to read it from the disk. So the overhead is not for splitting the data itself, but trying to aggregate the output and the getting to the next iteration.
Yeah.
So that is the additional overhead of hard disk. That's it.
The other question is,
Yeah.
on the graphical units that
Yeah.
have processing
Yeah.
capability,
Yeah.
I got the impression that each of the little CPUs in your are very small, very simple algorithms. They don't have as much processing power as a big main CPU. Am I right, wrong?
No, in CPU you have 4 cores. 4 cores have equal power, or for quad core or 8 cores.
Right.
Each core has equal power. But whereas the cores you have within multiprocessors in the GPU environment, that core is very, very small. It doesn't have that much power, right? Yeah, it doesn't have the same power as.
So it might be just very simple steps.
Very-
And somehow
Yeah.
the master has
Yeah.
to distribute
Distributed to the small. Yeah,
Or the
exactly.
workers.
Yeah. So those are excellent questions, because the next part of the talk it's going to address all these issues, and probably you can ask all of them if it doesn't address all the issues at the end of the lecture. Okay. Okay. So now the second part of the talk. Hopefully I will be done by 5. But I mean, if it's until 5:15, please don't blame me. Feel free to get up and leave at 5 o'clock if you really want to or have to. Okay. Okay. So that is about the first part. So the second part is about the k-means and k-NN clustering and classification algorithm. So the codes are available in this website, the same website. And the reason why we chose is, so let's start with, so in data mining, basically there are 2 areas of research. I mean, there are additional areas, but one is classification, the other is clustering. In clustering, data clustering is about when you collect data, you really want to find some patterns in the data, when you want to find some groupings in the data. So you want to simplify the data by identifying some groups in the data, right? So that is about clustering. Classification, on the other hand, you try to model the data to see how we can, how for a given instance, what will it do in the future. So you have some, in the classification context, you have some knowledge about the data itself and what group the data belongs to. And now in the future, given a new data, you can estimate or you can predict, you can forecast what category it's going to belong to, right? So for example, you can have news articles. That's a very classical application for classification. So each news article that you can see from LA Times or New York Times or Detroit Times, you will see that when you are given a news article, each article can have a category, like it might be talking about sports, it might be talking about music or politics, and so on and so forth. You are giving a class label to this particular document. If I have enough documents where I know which category this belongs to, then given a new document, I can automatically classify whether this document talks about sports or politics. So that is about a class label. So in a classification problem, given enough data and their corresponding class labels like sports or politics, which category it belongs to, I can build a model. I can then categorize any new document to belong to a particular category. Okay, so that is the purpose of a classification. Clustering, on the other hand, doesn't rely on these labels. It just says, okay, if you have these documents, maybe this Google News is a classical example for document clustering, where maybe a particular same announcement yesterday, maybe the Arizona results yesterday, everybody talks about it. Most of the newspaper talks about it. And when every newspaper is talking about it, you will see some overlapping terms. Okay, he said that, he said this is the caucus result or the primary result, and so on and so forth. Based on this similarity within the document itself, it's very hard. The classification, one of the drawback is, it's very hard for somebody to sit down, read the document and categorize it into, it's a politics document or a sports document, because somebody has to do that manually. Whereas clustering, on the other hand, saves this problem because you don't have to waste so much time. All it does is, okay, these two documents, the same news from yesterday, that would have been published in a LA Times or a New York Times, all these newspapers. You don't have to classify them, but all you have to do is just, because these two have a lot of similarity, you can group them together. And then you show in Google News, you can see that, okay, the main news article will be this, but there are similar articles to that covers the same topic from different newspapers. So you will have a representative point which shows the actual document itself, and then you have a group of documents that have very similar, because every day somebody doesn't sit down and reads all these newspapers and give labels. That's practically impossible, infeasible to do that, right? So data clustering, on the other hand, this is just for somebody who is not familiar with these two terms, data clustering and classification. You have some features about the document, about the patient, about the particular subject, or any object, any entity. You have certain features that you collect. If you just have this feature space, you have some description about these features, you can do clustering on it, you can find some groups of the data. Okay? If you do have more information about what category each instance belongs to, then you can do a forecasting of given new instance, I can forecast which category it belongs to. So these are two different things. Depending on how much you can get the labels, you can either do the grouping of the data, which is the data clustering, or you can try to forecast in the future by building a model, which is the prediction problem. So we chose the k-means clustering is a very, very simple algorithm. At the same time, it has a very rich history. And so for k-means clustering, the way it works is, as I mentioned, there are no labels in the data. It has only the data itself. So typically, let's say this is a two-dimensional data, and you are trying to find groups in the data. Right? The way the k-means clustering works is you start with some random points. So the plus markers over here are random initial points. And the way we colored it is, for each instance, we try to see out of the, so now the assumption is, I know that, so let's try to find 3 groups in the data. So if 3 is given to this k-means algorithm, now I want to group this data into 3 groups. I want to find 3 groupings in this data. The way this k-means clustering algorithm works is, for each of these centroids, you try to find for each instance which of these points the plus markers are closest. So the ones that I indicated in blue, all these blue points have this plus as this data point, this what we call as centroids of the cluster. These are representative points of the cluster, right? So for all these blue points, the plus marker over here is the closest. For all these green points, this is the closest, and for all these red points, this is the closest. So this is, once you have these initial representatives that I chose randomly, I now assign all the data points to the closest representative point that I can choose. This is the first step in the k-means clustering algorithm. Okay? So once I do that, now I can now change the representative point, because now I can see that most of the green points are over here. Now this plus over here is not a good representative. So I may have to move the representative to the center of the cluster, which is somewhere over here. Right? So in the next step, so this is where the iterative algorithm comes in. After the first iteration, where I have made this assignment, I need to change the representative points again. And then by changing the representative points in the next iteration, as the representative points changed, the points that were assigned to this one became farther from the previous iteration compared to this one. So all these assignment also changes, and these points come closer to this one, and so these are assigned to this point. Okay? So as the iterations progress, you can see that the representative points change, and eventually this is a final clustering solution you get. So given that this unsupervised data where you don't have any labels, I started with saying, okay, let's say three clusters. I assume that I know that there are 3 clusters, but I don't know what are the most representative points, or most importantly, which cluster does each point belong to. Now you can think of this as a very high dimensional space where each document is represented as a dot, and you are trying to find what is the most representative document, and all these documents have very high similarity to this document as opposed to all these documents which have high similarity to this and so on. So given this unsupervised data, I call it unsupervised because I don't know what categories. I just started with the data itself, where I don't have anything about the labels of the data, and I started with there, and I started randomly choosing the initial centroids, and then assigning the points, and I keep iterating this process. This is a classical example in data mining or data analytics applications where algorithms wherein you have an iteration process, and this iteration is known to converge depending on the algorithm, depending on the data, depending on the complexity. It can converge as small as 5 iterations or 10 iterations, or it can take 100 iterations. Okay, but this is an algorithm which is heavily used, and the reason why we chose this algorithm is so the overall algorithm looks like this, and I will explain why we chose this algorithm in the next slide. So basically, initial random k training data points as centroids, and then we do these 2 steps where I compute the distance between each data point and assign this data point to this centroid. Okay, and once I have the assignment all I'm saying is the coloring of the data. So I assigned, so in the second iteration, basically I'm saying this data point should belong to the second cluster, this cluster. These data points should belong to this cluster. So that is the assignment step. I'm assigning each data point to the closest representative point, which we call as centroid in this case. Okay, this iteration is known to converge, and finally you will end up getting the final clusters. So in terms of the actual pseudocode, you will see that you have these 2 steps where you have the random initial centroids, and then you take the assignments, and then you recompute the centroids, and you iterate these 2 processes. Okay, very simple algorithm, very powerful in many applications. This is one of the first algorithms. This started almost 1960s, where it gained some popularity. So since then, if you have to live with one data clustering algorithm, that will be k-means clustering algorithm. So this is so fundamental. And the reason why we chose this algorithm, so this is about the example, and if you are interested, I mean, I think you have the handout to look into the codes, so I just want to move on. So based on the k-means clustering algorithm, so this is the fundamental algorithm because there are plenty of other algorithms out there. Now data clustering is a very, very dynamic field. There are many algorithms. Each and every data mining conference I go to, we see new data clustering algorithms. So we had a book on data clustering, and there are many different data clustering algorithms. Most importantly, why k-means has to be emphasized is because when you have new data sets where you have, let's say, document data, it has its own structure. Let's say time series data, it has its own structure. Whenever you have network data or any kind of new data-based application, the first thing people try out is to see how well k-means does. Okay, so k-means has become like a benchmark in any of these new applications where, okay, if k-means can do the job, let's not go beyond. Okay, so based on k-means, everybody decides whether how far we should invest on developing new analytics algorithms or new clustering algorithms. So if you look at any of these scenarios, data streaming applications or domain applications like document data or biological data or the time series data, network data, all these data applications, the first algorithm to be proposed will be a k-means based algorithm. After that, people talk about a lot of other things. So this was a recent book that we edited with IBM, a researcher that I edited in the recent past. Most importantly, why k-means algorithm is a good example or an illustrative example, or I would call it as a representative algorithm for understanding the power of big data. You will see in the next 20 minutes where I talk about implementing k-means on these big data platforms. You can easily see what are the advantages, what are the disadvantages of the platforms when we understand k-means clustering algorithm thoroughly. So that's why if you haven't have background on k-means, if you have any question, please stop me now. And the reason why we are choosing k-means is because of the iterative nature. As I said, it can take 10 iterations. So now you can see the comparison with Hadoop and Spark, how important is the iteration and how much the performance is affected in the iteration context. And when we talk about assignment step, in the k-means, when you do the assignment step, when you try to find for each point which is the closest centroid, of all the 3 you are assigning the data point, that is a distance computation step. And the distance from one point to the other point is independent of all other points in the data. So this is a very easily parallelizable step. So now you think of this example, and you think, let's say you have a million points, and I have 3 clusters. Now for these million points, I don't have to do this sequentially. I just have the goal here, the assignment step. The goal is to find the million points, what is the closest centroid. So I take each point, I take the distance from all the 3 centroids, and I have to compute the distance, and I choose the centroid that is the closest. Right? For these million points, the simplest way to do it is if I have 10 machines, for all the 10 machines, I send all the 3 cluster centroids. And these million data point instances I have, 1/10 of it I send it to the first machine, 1/10 I just parallelize it, the data. So many of these applications that we talk about in analytics algorithms, the parallelization is very simple because most of them you will have to do things that are with respect to the data. And when data is million records, that part is easily parallelizable. I will show in many other applications where this phenomenon exists. Right? So no matter, even if the algorithm is sequential, when I say sequential, it really means I cannot move to the 3rd iteration. I cannot do any computations in the 3rd iteration unless I know the iterations result from the 1st iteration or the 2nd iteration. Right? That is what sequential means. So I cannot do anything in the 3rd iteration unless I have the 2nd iteration result. So that is what sequential means. So assuming, so if you look at k-means itself, it might appear sequential. But if you look at the details of each step in k-means, that is easily parallelizable. So that is one of the main messages that I want to take, because people say easily that, okay, k-means is sequential, iterations, so you cannot do. But usually in practice, it's not about the iteration result to iteration result. More importantly, within the iteration itself, the computation power, whether you can parallelize that component or not. Okay, so this is where the parallelization can be done. And obviously, when you have, in the GPU context, when you have 2000 cores as opposed to 4 cores in CPU, GPUs will do better, because if I have 1 million records where I have to compute the distances, if I have 2000 cores, the number of distances that each core has to compute, when I have only 4 cores versus 2000 cores, so you can see that when I have to compute these distances, GPUs will do much better, if that is the only goal for parallelization. So that is why this is a very important algorithm to understand. Of course, we have pseudocodes of all these algorithms, and I will explain each and every step what is done in each of the platforms. But I want you to really understand what k-means does in each step, because then only you will be able to appreciate why each step should be done at a particular component within a platform, not in the other way. Okay? So if you haven't heard about k-means, or if you are not following what I said, please stop me here, because everything I'm going to say will depend on your understanding of what you had seen just now. Okay. So the last one is the algorithm is parallelized, and there are this. The other component is within an algorithm. There are certain things that are compute intensive and certain things that are not compute intensive. For example, centroid computation, where you try to average out all points, is more compute intensive. Sorting of the data is more compute intensive. Just comparing distances, trying to find distance between one point to the other point, is not compute intensive. Right? So it's important to understand within an algorithm what is compute intensive and what is not. Because if it's something is compute intensive, especially in the GPU context, you have to do that part in CPU, because each GPU core is not meant for compute intensive tasks. So in the algorithm, you need to abstract what is compute intensive and what is not. If something is not, so in this algorithm over here, when you are computing distance from one point to this plus, or distance from this point to this, is just a Euclidean distance. It's a computation is very simple to compute. So you don't need very high processing power to do that. Right? So that part you can really parallelize, and because it's not compute intensive, GPU can do very well in terms of running it in a multiprocessor, with the core within multiprocessor. You don't need a powerful core like a multi-core quad-core CPU to do that job. Right? But when you have average of the data, when you have to summarize the data, average it out, sorting operation, these are not easy to do. So these are compute intensive operations. So making a multiprocessor do that job, it's going to have more overhead. So you don't want a compute intensive job to be done by a multiprocessor or within a GPU architecture I'm talking about. Okay? Yes?
You said you have a million data set.
Yeah. So that's a trial and error. So because if you have no idea, so remember that k-means is used to reduce the complexity of the data. So you have some understanding of, maybe if I have 1 million records, let's try to see if I can do 10 clusters. So that 10 is an input to the algorithm. And if 10, the result is you are not satisfied with the result, then you increase 10 to you make it 15. You run the algorithm again. So typically the number of clusters that which is a you don't know offhand. You will see the advantage by adding, when you add more and more clusters, you have an objective function called sum square error which is reduced. As you add more and more clusters, your groupings become more and more purer, right? Because if you have a very heterogeneous or more groupings of the data, you had only 3 clusters. Maybe different data points are forced to put in the same cluster. But if I had 20 clusters, maybe it is a more good cluster. So if you make it 50 clusters, then maybe you are happy with the 20 cluster result and you don't need the 50 cluster result. So when you add more and more clusters, so this you have to keep on trying the results with each and every number of clusters. So I say 20, okay, you are satisfied, then we can keep quiet. Otherwise, if it's you are not happy, then you have to go with 30 clusters in a 1 million record. Okay, so this is basically trial and error. Okay, yes?
So how do you decide on the dimensions of your vector? Like, is there a rule? Or
That is given to you. So the data is, you are collecting the data. So here I said 2 dimensions. In document data, you clean up the data, you treat each column, you put each feature, right? So you have characters. So if you want to group people, right? You take hair color, or you take the length of your hair, or all these characteristics, and then group them into people. So when you are given the data, you assume you have some features that you describe each instance with, right? So now you can construct a matrix where each row is the instance, and each column is the attribute or the feature that represents each of these instances. So now you have this matrix. And now in this case, I'm showing a two dimensions. So you have 2 columns, and maybe you have 50 points over here. So 50 rows and 2 columns. And now you are trying to, basically the goal of this is to identify for each instance, each row. In addition to 2 columns, I have to put the 3rd column and say, this first instance belongs to the first cluster, second instance belongs to the 3rd cluster. So now I want to give label at the end of the clustering that each of these instances, which cluster it belongs to. Right? Yeah. Yes.
You still have to know your data a little bit.
Yeah. So, I mean, what is given to you, you need to process it and try to put it in this matrix form. But for that, you don't need a domain expert to tell about the data. You just are trying to process the data. That I don't need a demo. I have this, okay, this is the data given to me. I have no knowledge about the domain. I still can do the processing and formatting of the data. In fact, I don't want the domain expert to bias my formatting of the data, because then I get biased results, right? So, of course, domain expert can help in improving the formatting of the data, but usually this formatting is independent of the domain expert, or it can be done independently. Because of that, we still call that as unsupervised. When the domain expert tells me, okay, this patient is more risky, right? Then that becomes a label of that patient, right? Yeah. Yes. Yeah. Yes.
So the selection, the identification and selection of the different features, that's just dependent upon your knowledge of the data.
Yeah. Usually there are.
What data is available.
Yeah, there are usually algorithmic ways to do it. Maybe some features do not change across all the, then they are going to reduce the performance of a clustering algorithm. So if features do not change for all the instances, then there is no grouping. We don't have to include them. So some features you can eliminate them just based on algorithmically. You don't need the domain expert again, right? Domain expert can tell that, okay, this feature don't use it, right? But he doesn't tell, okay, this instance he doesn't talk anything about the instance, but okay, these features do not make sense. That we are talking about columns. So when we talk about columns, I mean, domain expert, it always is helpful, or you can do some data cleaning. But domain expert doesn't involve in each instance and giving labels to the each instance. Yeah. Okay, any other questions about the k-means clustering algorithm itself? Because if you didn't understand that, it will be next, what I'm talking about in the next 10 minutes will be Greek and Latin to you. So, okay. Feel free to stop me if you don't understand.
Can you give an example
for
the k-means?
So this is the example, right?
Let's a real life example.
As I said, I mean, even every night you see a lot of newspapers releasing news, right? So each document is a data point. Each document has words. These words are features. So some documents, so these are columns. So each document is an instance. So these documents, usually Google News, Yahoo News, all these websites go after all these newspapers which release news, because they want to give Google News a summary of all the newspapers, basically, right? So now each document is a row, and you want to find which documents talk about similar content. When I talk about similar content, the distance between these two documents is very small. How do I define a distance between two documents? When these two documents have some lot of overlapping terms, so the terms in these documents will be my features. So each term here will be a feature, and if this term exists in this document, then it will be a 1, or maybe if it may be 5 if it occurs 5 times. So now you can construct this matrix where each document is a row, and each column is a term that is available in that document. If it is available, it's a binary matrix, or it can be a non-zero or positive non-negative matrix where it can be 0 or 5 or whatever. So once you have this matrix, now the goal is I want to find which two documents are very similar to each other. Then this whole thing comes in. Instead of just worrying about two-dimensional space, we are going to have 10,000 dimensions because 10,000 terms will be there as my columns. And we are trying to find the similarity between the documents in this 10,000 dimension space. Now I can find which two documents are more similar by just taking the distance between these two vectors. It's just a matter of vectors. So from the domain point of view, to convert to a matrix, we can do some processing so that we have to convert, because all these algorithms, everything usually works within a matrix form. So once I convert to the matrix form, then I can find the groupings within this matrix. Right? The goal is eventually you have these documents. I can say, okay, three groupings. So this group of documents talk about sports. These three group of documents talk about, and if you want to split even further, these documents talk about baseball. These documents. So you can find the groupings as long as you have this matrix form. You apply k-means algorithm with 3 clusters, or 5 clusters, or 10 clusters. You will see documents in a cluster have very close resemblance, because there are a lot of overlapping terms. When you have overlapping terms, the distance between these two components in the same column will be 0, right? Because you have the same term appearing. So as you have more and more terms overlapping, the distance between these two documents becomes lower and lower. Right? So then you can do the grouping of that. Okay. So that is about k-means. So now let's get into the k-means, the pseudocode part. And these steps, let's see how it is done on all these platforms. So for the platforms, what we had is, so in the platform set, what we had before, in this list, the peer-to-peer network was not available. Firstly, everything we have done is on Amazon EC2 cluster, because it's very difficult for us as as a professor to buy all these platforms. Okay, so the Amazon, most of the cloud computing software, no, that's reality, right? So but of course we don't want to give up the research, because so there is this Amazon EC2 cloud computing platforms, or even Microsoft Azure. Most of them are coming up with their own cloud computing platforms, and all these cloud computing platforms have some of these big data processing platforms. So in terms of horizontal scaling, there's no way that we can do the peer-to-peer, because peer-to-peer is about million machines through the internet. The Hadoop and Spark are available, and it's very easy to use. Actually, my student was able to dig it out within a day, how to use it, and then the usage, installation, everything becomes very, very user-friendly. So you don't need to, if you buy a GPU, you will have more things to install than just clicking an instance in cloud computing. So if you are not doing it in a long-term basis, if you just want to run and see what happens, I highly recommend a cloud computing environment, either from Amazon or Microsoft or whatever company. Okay. And then in terms of the vertical scaling platform, HPC was very difficult for us to get, and it's not available in any of the cloud computing platforms. So we did GPUs, and FPGA we are not even interested, because that's a very highly specialized for particular application. So we are not really doing that kind of. And it's, by the way, FPGA is not meant for all applications. Also, there is one specific, some specific applications where algorithms where FPGA is beneficial. And we took, for vertical scaling, we took GPUs and multi-core. So I will give all the details for all these platforms, how the k-means algorithm can be parallelized. But you will see, once you understand one particular platform like GPU, you will see what I'm really talking about, and how to do it in CPU will be very obvious to you. Though I have all the pseudocode, I'm not going to go through the pseudocode and steps of all the things, but at a high level I will tell what's really happening with respect to the k-means clustering algorithm. After we are done with this, we will do the same thing for a KNN classification algorithm, one classification algorithm. So these two are the representative data analytics algorithms, because they're kind of powerful, they're popular, and they're heavily used in many applications. So we chose these two are very good applications. By the way, before we started this work, there's not much work comparing platforms for these data analytics work. This is one of the first works, and when I discussed this with editors, I mean, they're really appreciative of this work. So it's something new. It's not very easily available available in many of the existing literature from the academic point of view. Okay, so in terms of k-means algorithm, so I assume everyone is having some idea about k-means by now. So now let's start with each, the three components, as I said: iterative nature, ability to parallelize, and things that are compute intensive and things that are not. Okay, so those are the three. Keep these three things in mind because we will go through each platform and say, yes.
Just one more quick question to back up a little bit. K-means implies because you've taken the average or the mean of something, and that these are all parametric or variable data, and not categorical data. In other words, you're not.
Usually for categorical data, there is a version of k-means called k-median. So usually when you have categorical data, there is k-mode algorithm, k-median algorithm. So usually k-means, because it's very difficult to get, and in fact in categorical there are other clustering algorithms that can do better in categorical data. So in fact one of the chapters in now my book deals with categorical data itself. So k-means usually we mean where you can take the mean itself.
Variable
data. You can average it out or
rational numbers or something.
Sure. Okay, so let's start with the GPU, and so here is the GPU code, and I don't want to go through the code. I will explain each step in this code through the picture, so it will be much easier for you to understand what happens. So in a GPU environment, as I said, there will be this multiprocessors, each multiprocessor having these cores, and these are connected to the GPU memory. So this is the specialized component, and in fact some of the CPU machines also have come up with this GPU slots where you can put the GPU, and then there is the standard CPU and CPU memory. Okay, so in this case, what happens is the first one is to initialize the first k data points. You can choose random data points as centroids. So in our case, we just chose the first k data points as the random centroids to begin with. Okay, so they are available in the CPU. They are now sent to these centroids, and the data is now sent to this GPU shared memory and split the data into threads. So as I said, now think about these multiprocessor are the cores. And so if I have 1 million records, I have 2,000 cores available in these multiprocessors. I will just split the data, but each of this core here is going to take all the three centroids. So just for simplicity, I have this 1 million records, and and I have 2,000 cores in the multiprocessor, and each one will have 50 instances, or 2,000, so 2,000 to 50, so 500 instances. Okay, so each of the 500 instances will be split into these cores. So 500, next 500, and so on. And each one also has the centroids, the three centroids. Okay, so now each one will do for each instance here. It will compute the distance from each instance to each centroid, and it computes that part over in each of these cores. You can see the power of parallelization, because now you can do this tens or hundreds of times faster than a multi-core machine where you had only 4 cores. Okay, that is where the power really comes. Once I compute the distances, so that is where once you have the thing, so that is where this kernel compute distance between the data points and each centroid. So once you compute that, now this is for the first iteration. So first iteration you computed that, and then you send it back to the GPU memory and send the distances. Now once again, remember that when I send it back, all I'm sending is not the features. The features were sent directly once here. The data is not sent back to the memory. All I'm sending back is the instance ID and the distance to the instance ID. So instance ID, I have the first instance, first centroid, what is the distance? First instance, second centroid, what is the distance? So only that is being sent to the memory, because the actual data instance itself lies in the CPU itself. So once I have that computed in the GPU memory, so once I have the distances, now it goes back to the CPU. Remember CPU, the centroid computation, where I average out all the points, is a compute intensive task. And I don't want to do that in the multiprocessor, because these are kind of slow to handle that thing. So the compute intensive task of computing the centroids for each of the cluster, wherein I have all the distances. So now I have these distances and IDs, I have the original data I have. Based on that, in the CPU memory, we can compute the new centroids. Once I have the new centroids, I pass it on to this multiprocessor again. And then this is for the second iteration. The data remains the same. I don't switch data again and again, because because the data switching is the massive thing. I have 1 million records, and assume I have 10,000 features like the document thing I talked about. This data is massive. I do that only once. And that is a very critical component. And because of the number of processors I have, I can just take this and do the simple computations. So the bottom line here is the simple computation part, you do it in the multiprocessor, GPU multiprocessor, in the course within the GPU multiprocessor. Compute intensive task, you do it, and you do it in the CPUs. and don't keep transferring heavy amounts of data. You still have to transfer the data, but the data is just the index IDs, instance ID, cluster ID, and the distance itself. That is much, much smaller than 1 million records was 10,000 columns. So that is not being transferred much often, right? So now the CPU, we compute and sort the distances in the CPU. That is trying to identify which cluster centroid each data point should belong to. What is the closest centroid for each data point. And once I have that, I associate each data point to the closest centroid, and I recompute the centroid, which is the average computation step. So this part where we have sorting the distances and recomputing the centroid is done in the CPU main memory. And once I have done that, I have the new centroid information. The data remains the same. I have only these 3 new centroids I have that I will pass it on to each of the clusters. I recompute this step again with all the 1 million, which is for each of the 2,000 cores, 500 samples. I compute the 3 for the new centroids, and I get the distances. I update the distance over here. So you will see that what has to be sent to the GPU and how many times the data should be transferred, and what is the compute intensive task. These 3 are the critical components for any data analytics algorithm when you do a big data platform. And in fact, I would argue that these 3 are the most important ones, and all other things are at least maybe application specific. They are not as critical as or as widely needed as other requirements. So what I'm saying is these 3 issues appear in most of the applications. Maybe you have some specific need for your specific application that might not have been covered over in this particular algorithm, but many of the algorithms have this iterative nature, have this compute intensive part, and have this parallelization part. Okay, so these 3 things with a GPU environment, you should know where to do what and when to do what. Okay, that is the main message I'm trying to get to you in today's lecture. So that's why I'm kind of emphasizing that part. If it's obvious for you in the first step, please pardon me on that. Okay. Okay, so that is the thing. Now, the reason why I'm also emphasizing on GPUs, because once you understand GPU, CPU becomes a cakewalk. Because once you understand how GPU is done, the CPU part is, you replace this. In CPU, you don't have that luxury of parallelization. So you replace this multiprocessor with the 4 cores I have, right? And you treat 1 core as your CPU, and remaining 3 cores as your cores within the GPU. And so parallelization part is poor, but you can do a lot of data intensive things or compute intensive things within each part, right? That is the reason why GPUs are usually preferred. If your data is limited or you don't have terabytes of data, when your data is limited, because of the ability to parallelize so fast, and the fact that this memory transfer, this is with DDR5, this memory transfer is fast, then what else do you need? You need more parallelization. The I/O transfer is very fast. That's why GPUs are gaining a lot of popularity, and usually they do much better than a CPU computation. Okay, so that is the main message that I really want you to get out of this process. Yes. Okay, let me finish the CPU and then I can take questions. But the CPU is kind of obvious, where obviously multi-core. So I have 4 cores instead of this 2,000 cores in the multi-processor. So the amount of parallelization I can do, and it really follows the same style. As I said, 1 core, the first core you keep it as a CPU, and all other cores you treat it as the multiprocessor cores that you did in the GPUs. Okay, compute the centroids and then distance to the centroids and recompute the centroids over here. Exactly the same process, just that you treat 1 core as your CPU and all other cores as your GPU cores, like what I just mentioned. So you know how to parallelize. Once you parallelize, you get the results. There is not much change in that. Yes. Yes, you had a question.
How easy was it to use GPU?
Oh, that is a tough question. I mean, that my student has to answer that. But it was not that bad. People have the impression that GPU codes are very. First of all, I mean, I will go towards the end where Amazon EC2 is a wonderful platform. Again, I'm not getting any amount from Amazon. But one thing I have to acknowledge is that all these platforms, Amazon, I didn't pay anything to Amazon. So when we said we want to do this project and we want to compare platforms, they were nice enough to give me for free. Okay, so in the Amazon, the GPU platforms, CPU platform, creating a new instance is not at all difficult. Just that you have to write some code within the GPU CUDA environment, and you upload that to the cloud computing. It was not that difficult. I can tell you that. Okay, it was not as easy as you write it in multi-threading code, but it was not, because people have this impression that GPU code is very hard. As I said, that was in the past. When CUDA programming doesn't have many wrappers, you have to write a lot of hardware details in the code itself. But now GPU coding has become much easier because of the CUDA programming, and these are becoming wrappers to deal with hardware level details you don't have to do. It's a different syntax, so as learning with Hadoop or Spark, you have the same kind of new learning curve to write the code, but it's not about dealing with a hardware or anything, even if you write any GPU code. Okay? Okay. Is that okay for the GPU and multi-core? Okay, so because I really want to get some message out here, I mean, it's not just I'm having this tutorial and yeah. Okay, so the MapReduce part. So the k-means, the MapReduce is a popular paradigm. Again, it does parallelization. Now think about this. MapReduce and Spark are the horizontal scaling platform. So what we said, GPU and multi-core are vertical scaling platforms. So the MapReduce and so the Hadoop, this is MapReduce on Hadoop environment. So again, I mean, this is the pseudocode, and we decompose this problem into two pieces where you have this mapping portion and reducing portion. If you remember the first part, we had the partitioning and combining. Now you can see how k-means can be done by partitioning and combining. If you understand the k-means algorithm, you can obviously very easily see. I will show you in pictures. I don't want to miss anything here. Data instance to clusters, compute the new clusters, reducers, aggregate the step. Yeah, I am not missing anything. Okay, so a Hadoop architecture, you have this HDFS file system that I mentioned. These are where the data is being there, and you have multiple machines, mapping machines. Again, all the centroids go to each of the clusters. This is where the parallelization occurs. Maybe I have 20 machines or 100 machines to do the mapping. And these are more powerful machines, so the computation does very fast. So I have each of this, so let's say I have 10 machines over here. So Hadoop is an environment where I have 10 machines or 20 machines, number of machines. And each machine, I send 1/10 of the data, right? And all the centroids. So once I do that, I compute this, I compute the distance from each centroid to each point within each machine. So this is where the parallelization comes in. And once I have that, I do this, the mapping part where they compute the distances, and so the output of a mapper usually is a key value pair. So key value pair is basically for each ID, I want to find a value. So key is the ID. So in this case, what we give as you have this lesser than symbol, key, comma value, and a greater than symbol. So this is what a Hadoop mapper output is going to come from each of the mapper functions or mapper machine, right? So once I have that, now the outcome of this will be, so over here, the key value pairs with key as centroid ID and value as data point ID and distance between them. So over here, this is a small thing that it is still very important issue, where I have these machines and I have the distance from each data point to each centroid, okay? Now I send the centroid as my ID. So I take each centroid and I take the data point ID and tell what is the distance. So these three components, I can represent that as a tuple of key value. Key is the centroid ID and value is the instance ID and the distance of the centroid to the instance ID. These three values is a key value pair. I send it over here. The reason why it is important is because now I have decided this shuffle and sort. For each centroid, this place I will identify what are the centroid, what are the data, this is the assignment. So now once the mapping part is the parallelization part where I compute the distances, mapping part, and then once I compute the distances, for each centroid, for each instance, what is the closest centroid is what the assignment step. So I take each centroid and I sort the distances for each ID to each centroid, right? And I do that sorting part in the shuffle and sort. This is a very common step where I try to sort the IDs, the key value pairs. Based on the key, I sort the values and I associate the reduce step. In the reduce step, what happens is, so let's say centroid 1, I know what points are assigned. So reduce step, centroid 1, centroid 2, centroid 3. I know what data points come in here. So that distances, and then I take the average of, once again, the data is available over here. So I take the average of these distances and I recompute the centroid in each of the reduce step. You can see that mapping is the parallelization or the partitioning step and reducing is the aggregation step. So the aggregation or combining the results, wherein I have the distances from the centroid to the distance or to the data points. So I take for each centroid what are the data points assigned to this centroid, and I recompute the centroid over here. Once I have for the first, this is end of one iteration. Once I have the new centroids for each iteration, for the first iteration, I send it to the disk, I write it to the disk. Once I read the centroids again to the disk, and for the second iteration, from the disk, I read it to this new, and I do the recomputation over here, and the assignment over here. Okay? Assignment step is done in the shuffle and sort, and the recomputation of the centroid is done over here. Each iteration, you will see the three components of the parallelizing the data point, computing the distances, and the assignment of the data points to the closest centroid, and recomputing the centroids over here in the reduce step. Usually people call the reduce step to be all the things together. Shuffle and sort is part of the reduce step also. Right? But in general, these are the two main things in mapping, where you do the partitioning and the data intensive data computation is done in the mapping stage, where you have a lot of parallelization that you can take advantage of, and you combine the results in the reduce step. Okay? So you will see it has resemblance, but you think about it, it's not a single machine. We are talking about multiple machines. This node might fail. There are many practical issues that you get, that maybe this computation does very fast, and then you have to wait until these computations come, because you cannot do these operations until all of them. So there are practically, you will see some issues. And these are issues for parallelization in any context for that matter, right? Because at some point you have some serialization, but the most important parallelization you can do in the mapping step. Right? The critical component, that is where you really benefit in terms of the time. Okay? So the Spark follows the very similar structure, wherein you don't have HDFS. So forget about HDFS, you just write everything in the memory. And so this is the Spark pseudocode. I mean, I'm not going to go through each step in the pseudocode, but it's very obvious from my explanation each step what it does and where it does. Okay? So K-means implementation on Spark is very similar to K-means implementation on MapReduce. Only difference is in terms of writing the global centroids and the things that we already discussed. Okay. So now once you have the disk, it's everything. Most of the steps is done over here. Usually Spark you may do in MapReduce style, or you may not need MapReduce style. All of them you can do it in a single step on doing the distance computation, and you do it, write it, and so usually it is done on a set of machines just like this. Okay. So in terms of the actual message, how MapReduce does K-means and how K-means can be applied or developed, implemented in a GPU. So those are the two things I really want you to get out of this K-means part. Okay, because the K-means has these unique characteristics where parallelization, iterative, and the computation intensive part. So those are the main things that I want you to get. Okay. So now moving to any questions so far? Okay. All the details, codes, everything is available. Documentation is available. If you have the Amazon EC2 cluster or somewhere, you can get the GPUs. So all of them are available. So you can look at it on the tutorial website I mentioned. Okay. Okay. So for the KNN, so that is the clustering part. So I want to. So for KNN, it's a very simple classification algorithm. There are many classification algorithms like probabilistic models or like naive-Bayes method or the decision tree methods. Different classifiers are available. KNN is a very simple classifier, right? You don't build a model. So given the data, I just keep quiet. I don't do anything with the data. I just keep quiet until you ask me to find what is the label for a new document, right? So if you want to find a label to a new document, the KNN, the simplest thing is you don't do any modeling. You don't. It's just it's a very non-parametric approach. You don't build any model. You given a lot of like all the documents that I collected, I just keep quiet. I just keep it there with me. Okay. But once I get a new document and you're asking me what label it should have, right? That is the testing document. So for the test document, once you have the document, all I do is find out what are the nearest neighbors for this document in the testing phase, in the real. So it's not really good for real-time applications. So this algorithm. But what I do is, given this new test document, I compute the distance to all the documents available in my database. I take k is again a parameter. So I say, let's say I take the 5 nearest neighbors. So basically, I give the label of the majority of my neighbors. So for each data point, I compute the distance to all other data points. I pick the 5 closest neighbors. And if out of 5, 4 of them are saying it's a positive label. 4 of them are saying sports category, and 1 of them is saying politics category. I just say this document, since it's 4 of its neighbors out of 5 are saying it's a sports category, then I'm going to label this as a sports category. Okay? So there is no modeling, there is nothing we do in the training phase. Given massive amounts of data, we just keep quiet with it. Given a new document or a new instance, I try to find what is the closest neighbors I have in the database, and I try to give the label of the majority of these labels. Okay? Very simple algorithm, not good for real time, because you remember why it's not good for real time is because you have to compute the distances from now. Let's assume you have given me already million records. I have million data points already in my database, and given a new case, I have to find the distance from one data point, test data point, to all the million distance. And I have to do this after I get the test database. So usually when you provide the database, you don't have patience to wait for a long time you need the result very quickly. Right? So because of that, k-nearest neighbor is not good for real-time applications. But it is still very, very powerful because you don't have to do anything with the data. As opposed to machine learning methods like support vector machines or neural networks or deep learning, where you invest heavily in building very complicated models, nonlinear models, very complicated models. You don't have any model here. You just have to compute the distances. And if you can do this distance calculation very fast, then the algorithm performance, the accuracy of the algorithm is very good actually. Compared to, it's almost in some applications, it can be compared to any fancy or the sophisticated algorithm. So the performance wise it's good, and you don't have to do much work, except that you have to compute million distances. If you are giving me million records, I have million distances, and I have one test data point, and I have to compute this million distances as fast as possible. This is where the parallelization can help. Again, for test point to distance computation, these are independent of each of the distances, and here you can see there is no iteration. There is just one snapshot. It's just a pure distance computation. There is tons of research. So first algorithm in KNN was published in 70s. And since then, there is huge amount of research in how to efficiently compute the distances. There are different data structures to do that, and the easiest way to compute the distances efficiently is just parallelize them. If you have a very good parallel environment, and you are trying to find, and again, distance computation is not the only thing. You need to compute the distances. You need to tell me which instances are the 5 closest instances. You need to get me that labels. And then you need to say, okay, because 4 out of the 5 are saying this is particular positive label, and that's what I'm showing here. If it's a binary problem, you have positive labels and negative labels. If you're usually, because we can take majority vote, and if it's a binary problem, you take odd number, either 3 nearest neighbor, 5 nearest neighbor, 7 nearest neighbor, because you don't want any ties. If I take 4 nearest neighbor and 2 of them are saying positive, 2 of them are saying negative, it's a disaster, right? So you basically go with randomness. After computing all the distances, then you have to go with randomness with being positive or negative. So usually you go with you go with the odd number. So 5 nearest neighbors, 3 out of 5 say this, then you go with that number. So that's what I'm showing over here. Okay? You can see that it has resemblance where you want to do parallelization. It's all about computing the distances from one point to the other point. And that part is where you parallelize. And you have, usually if test instances are few, training instances, the 1 million records I'm talking about is huge. And so you are computing the distances from each test instance to all the training instances. Right? So that is where the parallelization comes into play. Okay? So now that you have understood k-means, I can go, this one I will take it a little faster. And so this is the basic KNN algorithm, where I have the training data, I have the test data. Test data, let's think of this 100 samples I want to give labels. And training data, I have 1 million records that I already know the labels for. Again, this is all, we assume we have all the labels here. This is a supervised problem, or a classification problem is usually a supervised problem because we have the labels. And the first k training data points as nearest neighbors, and then assign the most frequent class labels as the. So basically, you take the distance. Let's just get into the GPU implementation. Right? So there are these 2 steps you can see. One, to parallelize, where you can parallelize the distance computations, and then you take the distance values, you sort the distance values, and you find which is the what label you should give, right? So in this case, let's go with the picture. So I have this first, I copy the data and the test data. So D is the training data, and X is the test data to the GPU shared memory. Again, the main important thing to note is compute the distance between DI and each XI. Each one has all the test instances. Each one we will give all the test instances depending on the size. and I split the training data into each of the processors. So for each test instance, I compute all the distances to all the instances within each core, each processor or each core, and then I compute this result and I send it back to the GPU memory. Again, the data itself is transferred only once, and all I'm transferring here is the test instance ID, training instance ID, and the distance itself. I'm not comparing 1 million records to all the features. So all the features are just sent once over here. I'm not sending back to the memory because the CPU already has that information. So once I have this distance information computed over here, I send it to the CPU memory, copy the distances of the GPU memory and split it into threads. And so now for each instance, now I will find, so copy distances into, okay. So now once I do that computation, the next step is to, for each instance, so now if I have 1,000 instances, I put it in the 1,000 cores. For each instance, I have the entire data and I have the distances to the entire data. Now I can sort which of the 5 are the highest. So now you can ask why the sorting is done in a multiprocessor, because usually sorting is a very computationally expensive process. So let's go back a little bit. I think there was a gap in. So in the first step, 1 million records, 1,000 test records. Okay, 1 million D is 1 million records with the features. So I put it over here for each of the test instance. So I have the 1,000 test records. So I take each of the test instance and train instance and the distance. I send it back. Until that point, I think that parallelization will take care. The next time, once I have that information, for each test instance, I know for all the 1 million records, what is the distance. I can aggregate that within the CPU. Right? Once I aggregate that, I have 1,000 test instances, and I have the distance of each test instance to all the 1 million records. That information, I will send it to multiprocessor here. And this job here now is, once I have one test instance, I have 1 million records and their distances for this test instance. I have to find what is the 5 nearest neighbors, so which is the 5 lowest distances. So that is really not a sorting operation, though we call it as a sorting operation over here. We really have to find the top 5 or the lowest 5 distances. So it's a linear operation. I want to emphasize that a sorting operation is n log n operation, whereas finding the maximum is a linear operation. So that's why I'm trying to get to that. Okay. For each, now the second time I send it back to the multiprocessor, I send for each core, I send one test instance. For each test instance, I know the distance of all the 1 million records. I pick the 5 smallest values, which I can do in a linear manner, which I can do it in the multiprocessor itself. Because the question comes, the sorting cannot be done. Sorting, averaging, all these things, multiprocessor is not good. Okay, that's what we started with. So here we are not really doing sorting. We are just picking the 5 lowest values, 5 closest neighbors. So we are just picking the lowest, the next lowest, and so this is just a linear, constant linear time. It's not a sorting operation. So now for each test instance, I take out of 1 million, I pick the 5 closest, I take the labels, and then you send it back to the CPU and assign the label to the CPU. So the 2 main components are the training data is parallelized, compute from the training data to instances in the multiprocessor cores, send it back. Now for each test instances are parallelized. For each test instance, find the lowest 5 distances, and you send that lowest 5 IDs back, and you label that for that test instance. Was that okay, or? Yeah. Okay, I tried my best. I think it was. I assume because once you understand the parallelization from k-means, parallelization here is very similar. Distance computation remains the same. Just it's not iterative. You just have to send it back to get the lowest. The sorting operation, you can still do it in multiprocessor. Because here, remember, in k-means you had only 3 centroids or 5 centroids or 10 centroids. Here, test instances can be 1,000. Even this can be parallelized. So that is the main point. The second time, you can still parallelize. Whereas in the previous case, you don't parallelize it again. Here, you do the average computation. You send to the second iteration. Here, you are not sending to the second iteration. It's the same iteration. You are just parallelizing the distance computation with respect to the test also. So the test is being parallelized. That is the main message and main difference from k-means implementation to the k-NN implementation. Okay. Was that okay to everyone? Because I mean, I really want to emphasize that, because again, once you understand on this point, everything becomes much easier. All other platforms, it's just a matter of different kind of coding style or different, but the core component of where to parallelize and what to parallelize is the most important thing. Okay? Yes?
One of the things you said is GPU is better than just dealing with multi-core processors, assuming that you're only kind of looking to parallelize and not trying to do things that are more intensive.
Yeah.
What is an example of something that's more intensive?
Where, I mean, if your data is low and you have more intensive operations like even centroid computation. So if you have only 1,000 samples, right, putting in 4 cores or 20 cores where the actual computation times is more dependent on the centroid computation or the part. So it depends on the data complexity. If the data is not very complex, you would rather benefit from CPU itself because each operation you can do very fast. So a CPU core, you can do it very fast. So this will benefit, GPU will be beneficial only when you have 1 million records because parallelization will overtake the computational power, right? So the parallelization will be more beneficial. If you have only 1,000 samples and you are trying to apply k-means, and each core in CPU, multi-core CPU is much more powerful. So you can do computations very fast as opposed to a multi-core, multiprocessor core. Right? So this is main advantage is because of the parallelization and sending it to the memory is much faster. Because of that, the GPUs will be better. Right? But when we talk about big data, usually we are talking about million records. So that's where I said GPU might be better. Okay. Okay. So any other questions? Yes. So in the interest of time, I will go through the other platforms very quickly, but I have other take-home messages that I really want to deliver here. So I just want to go very quickly. And at 5 o'clock, if you need to leave, you feel free to leave. I won't be offended. Okay. Same thing here. I don't have to repeat. The one multiprocessor, the parallelization is low. Each core, everything remains the same. Just that one core is used as CPU, and the other cores are used as multiprocessor cores. Okay. So I'm not going to dig into this, and of course we have all the details over there. Send it back, test instances, and so on. Right? Over here again in this picture, you will see the parallelization of the training instances is done here for each test instance. So once I have that, so read D here is the training data, X is the test instances. So the set of the test instances, each key value pair. Again, the key value pair is test instance and the training instance ID and their distance. So that is just like the centroid when we did the k-means distance computations. It's very similar, just that you don't need the iterations. And you will see that when you don't have iterations, the Hadoop and Spark performs very similar. Okay, the performance is not very different. So aggregate each with respect to the test instance. For each test instance, you find all the million records. Find the 5 smallest values. Get the labels and give the labels over here. We are done. Right? So that is how the MapReduce thing works, and then the Spark. So the Spark over the same thing like what we did in k-means. Okay. So there are other things that I would like to talk about, and in the interest of time, I mean this is some information I really didn't intend to talk about, but I just wanted to put it in the slides because this is good information that you know. But I mean I don't have to explain this. I mean this is just the advantages of Amazon EC2 cluster, easily controllable. So if you have you cannot afford GPUs or things and you want to test out, this is a good platform where I put the costs and everything. And other thing I want to mention is, so we did some experiments. So this is extremely easy to control, very reliable systems in terms of fault tolerance. So these are very huge advantages for using this cloud computing platforms. Very easily scalable and secure, inexpensive, easy to start, and so on. The cost-wise, I mean, also you have the ability to do this for compute optimized, so that if it's compute-intensive tasks, you have different kinds of ways to optimize for the platform, and there are this cost associated. So for our experiments, so I have this details of the experiments in the slides, and make sure you switch off them. Sometimes we lose a lot of money because when you don't turn off the instances, they are going to charge like anything. Okay, so you just forget, and after 1 month, you go back and you will see your bill coming skyrocketing with things. So make sure you turn off. So these are things that it's a good practice to follow. So these are not essentially things that you will benefit if I don't have to teach these things to somebody, right? So these are the instances. So we do have some experimental results based on the instances that we created. So these are the details of all the instances that we use. So just for the completeness of this work, I'm just putting all out there. One thing to note is that we make sure that all the platforms have similar costs. So per hour we are having 70 to 80 cents because it's unfair to compare GPUs to multi-cores if GPUs are costing $5 an hour and the CPUs you choose is costing less than $1 an hour, right? So we have to keep something constant when we are doing these experiments. So we made the cost is very similar. So it's 70 cents or 80 cents. And we ran a lot of experiments on the document clusters, all other lot of data sets. And the summary of the data sets are as follows. So in terms of the vertical scaling platforms, you see that this is the running time of the algorithms in log of this time. And as the number of features increase from 30,000 to 130,000, as the number of features increase, the vertical scaling platforms do much better. They don't take that much time. And the horizontal scaling platforms are kind of slower. But they have the ability to take lot of data, right? So over here, in GPUs or the multi-cores, they cannot run if it's more than 100K features. 100K features are the 100K columns I just mentioned, right? So they cannot handle that on the given configuration if the data is massive. And we talked about it. The scalability of horizontal scaling platforms is much better. If I increase the processing need for the vertical scaling platforms, they are not going to function well, right? That is the first take-home message. And just for comparison, the first single core CPU where you cannot do any parallelization is also given over here. This is the result of the k-means algorithm on document data sets. And this is just to increase the number of clusters. You see the variation in all the platforms. We take 70K features because all the platforms can handle up to 70K. GPU can handle up to 90K features. So we can experiment how much big data that these scalable platforms or vertical scaling platforms or the horizontal scaling platforms can handle, right? So in terms of the horizontal scaling platform, we really want to take it to the next level and said, okay, let's try out on the original data which had 50 gigs, right? So 50 gig of data. And you will see in the k-means context, with 50 gigs of data, k-means when we have the iteration part, the Hadoop does take a lot of time because of the iterations in k-means, whereas in Spark it does much, much faster. So in the iteration context, and if you have very high scalable, Spark might be the better option. So that is one of the messages over on this. And for the KNN part, you will see because it's not iterative, Spark and the Hadoop are not giving too much difference. This is the single core case, and obviously again the GPU and multi-core over here are much faster in terms of because of the parallelization and the fastness. Okay, so that is one of the take-home messages. So that's whatever I just said is given in this slide. And so the next part, this is the last 10 minutes, I would say. Just bear with me for 10 more minutes. I think we'll be done, right? So this is one of our, I wouldn't say recent works. I mean, like 3-4 years back, we did parallelization. So there is a very powerful algorithm in data mining called boosting, which is an iterative algorithm. We did parallelize that algorithm. And the reason why I want to show that is using MapReduce algorithm, where basically you try to partition the data, build local models. Once you have the local model results, you do the reduce and you do the computation in the reduce step, and you combine the results and you get the final results to the user program. And so this is the map step and reduce step. The reason why, so this is how the algorithm does. I don't have time to dip into the algorithm, but the message I want to really deliver is when you do the parallelization, there are many advantages, and we want to be clear what kind of advantages we get by parallelizing the learning models. When you are trying to do machine learning, building models, what are the main advantages that we can get? One is the scalability, and then the other is the speed, and the third is the privacy preserving. I have one slide about each of these topics, so let me go over it directly. So over here, let's talk about the speed up, because every time we talk about improving the performance, we talk about getting the results much faster, right? So assuming we get the same results, accuracy remains the same, we want a platform which gives me the result in much faster manner. What I mean by much faster manner is when I run it on more workers or more nodes. So if instead of running on one single computer, if I run it on 20 machines, can I make the result? Can I get the result 20 times faster? Right? So that is the overall goal of speed up. So speed up in definition is the ratio of the execution time on a single processor to the execution time on when I have identical P processors. So what we did is with the Amazon workers, we have the nodes. When I increase the number of nodes, in many cases, I see that the performance or the speed up is a very good metric to identify what is the amount of time that I save, right? So when I do this, because I do the local computations, when I add 20 machines to my work, I can do this 20 or 25 times faster in terms of if the original problem was taking me 1 day, I can do now in 1 hour, right? So that is one message that I want to. The speed up power is, and here it's usually if it's the same problem, because we are decomposing and changing the problem a little bit. Here we get 25 times better if I have 20 machines, but usually it will be 20 machines 20 times better. If you are solving the same problem, then you have 20 machines. You should at least you should reach 20 times faster. So that is about speed up. It is different from the other metric called scale up. Scale up is where you have a task and you are saying, okay, this task is going to take 1 hour, right? But what is the scalability performance of the task is different from the speed up of the task. Scalability performance of the task is if this task of building a classification algorithm on 1 million records, if this task is done in 1 hour, what will be the task if I give you 10 machines and I multiply this task by 10 times? So instead of 1 million records, I give you 10 million records and I give you 10 processors to do that. Will I still be able to do it in 1 hour? That is the scale up performance. Okay, so in the speed up, the task remains the same, time is reduced. In scale up, the task is multiplied, the number of processors is added, and you want to maintain, because at some point, if your algorithm has too many communications, and at some point by adding more processors, your communication costs dominate, and your 1 hour is going to take more than 1 hour. So that is the scale up performance, right? By multiplying, so the scale-up definition is the ratio of the time taken on a single processor by the problem to the time taken by p processors when the problem size is scaled by p. So instead of 1 million records, if I take 10 million records, will I still be able to do it in one hour, right? So that performance, the time ratio, how much time do I take? If I take 2 hours instead of 1 hour, then the scale-up is 1 by 2, right? It's half. So the graph, as you add more number of workers, because the communication cost dominates than the computational cost, you will see the performance goes down or the scale-up value goes down. So whenever you talk about performance in the parallelization context, these two metrics are very, very important. The speed up, how much time you are going to reduce, and scale up, how scalable is your models. Yes?
Sorry, what is the difference between the two charts?
Oh, okay. So these are two different, I think I should have explained, just in the interest of, so these are two different data sets and different algorithms. What we are showing is our parallel version of AdaBoost algorithms that we have. The scale up is very close to 1, and it maintains as the number of workers goes, it is still very close to 1.
So they're just
two different data sets. Yeah. Thanks for clarifying, but just because in the interest of time, I'm not going through. And we have a paper on this, and but in general, I mean, speed up and scale up are the most important thing. And you will see the speed up is this, right? This is obvious, right? When you have 20 workers, as the number of workers increase, then the speed up is going to improve in the same ratio, right? 20 times it gets better, right? Okay, yeah. Just 5 more minutes. I'm getting the clicks from there, so I really need to. Okay, so scale up. The other advantage of parallelization is we applied on medical records, and parallelization can also preserve privacy, right? So if you have a model, instead of sharing the data and building all the data from different hospitals, we build a model and the model parameters are sent to the central agent. So this local model and learning from local models can help in preserving the privacy, because this hospital should not know the data from this hospital, but the model that it learns can be shared in the central agent. So by building a local model, you will be able to do the privacy preserving angle of the big data, right? So you don't need to share the model, but you can share the model that you don't need to share the data from each individual local machine, but you can share the model that is built from the local machine. It's a very powerful method, and this is a paper that we published in this year actually. And the other message that I want to take, probably this will be one of the last ones, will be there are many works where parallelization is important. So if you take a linear regression model, very simple, very powerful, very heavily used in practice method, and you have the x and you want to find the parameter theta, usually the solution of it is a closed form solution where you can get the a and b. So ax is the original one, and then you have this b value. So once you have this a, usually most of the algorithms, I will show you in the next slide, most of the algorithms follow this standard, right? Where if I have 1 million records, I'm summing up the values of the data points and the distances in 1 million record. This summation process is applicable to most of the analytics algorithms. There is very rarely you will see an analytics algorithm where you cannot redesign the method in terms of the summation, right? So you can see, once I do this, once I can do 1 million record summation, I can parallelize this easily. So this component usually is parallelized in the analytics algorithm, where if I have to do for 1 million tasks, sum up 1 million tasks, if I have 10 machines, obviously I sum up with 10 machines, and then I sum up the values that I get from these 10 machines, right? That's a very natural way to do. So you will see that in the next slide, there is a classical paper from Stanford University professors Andrew Ng. He's a very popular guy in machine learning. They published in 2007 MapReduce method for different multi-core. They show that most of the popular algorithms, locally weighted linear regression, logistic regression, naive-Bayes, nearest neighbor method, Gaussian discriminant analysis, principal component analysis, independent component analysis, k-means algorithm, expectation maximization algorithm, and support vector machines. These are all the popular data mining algorithms. You will have that component of the X transpose that computation, where you have to sum this component for 1 million records. And you will see, by adding 10 processors, you can reduce the complexity of the original algorithm by dividing it by p, because the summation component, which is a very compute intensive task, you are parallelizing it across 10 machines. And you are taking the results of the summation of 10 machines, which is much faster than running it across it. 10 is just an example. You can run it on 2000 GPU multiprocessors, right? So that is just to show that many analytics algorithm, even though they claim they are serial, if you dig into the algorithm itself, there will be a lot of parallelization that one can do. And the parallelization example is over here, where you just divide the summation into this. Okay. So that is the other message that I really wanted to give.
What are the terms in the order statistic?
Oh, this is M is the number of columns, N is the number of rows. So M and complexity of the algorithm. And you divide that by P, when P is the number of processors. The number of processors can be 100 or 2000 or something. Okay? So this is where I really want you to leave with this message, and this is just the summary. I think this is just the summary. Okay, so the big data analytics is important, and the parallelization is the key component. So, of course, it's not just about the size. Real time is one other angle that people are interested. On different platforms, the main goal of the tutorial is to understand different platforms, their key strengths and weaknesses. Given popular analytics algorithms, what are the things that we can parallelize, or we can make things work faster, or do things in a much faster environment, right? So still big data analytics, as I said, this was an algorithm that was done for MapReduce, but nobody has really done any comparisons of these algorithms on real platforms like what we did for k-means or KNN. So that is one angle that one can look at to see in these algorithms there are more complexities than KNN is a simple algorithm, right? So there are more complexities than the KNN algorithm that I presented. That's a good data mining or big data projects that one can think about if you're in academic environment or as a student, right? So that is one thing I really want to create. And there are many, in terms of industry, our expertise is on healthcare. There are a lot of healthcare big data challenges in healthcare, sensing data or signal data. Genomic data is massive, 3 million SNPs, 3 billion SNPs available. Clinical notes and big biomedical literature is unstructured data. So textual data, it's also one form of big data. Prediction models, temporal data, where the patient you are following over a period of time. So we have a recent book on this topics, and some of the chapters on this are available from my home website. So if you are interested in the healthcare, this is one area where big data and healthcare can be really, big data technologies can be very useful in the healthcare domain. Okay. So I hope sorry for being a little late, but I should thank my funding agencies, and most importantly, I should thank my graduate students who really helped me put together this tutorial and publish these papers on big data comparisons. So 2 of the master students and 1 PhD student, they graduated, and PhD student is still with me. And, okay, so that's I should thank my NSF and NIH funding agencies, which are my primary funding source. And thank you for attending the tutorial. So I will be available. I can take any questions, and if there is a coffee break, I believe, so you can go.
For the regression, usually we use the gradient descent or instead of the normal equation. In that case,
so even in the gradient descent, you have to compute with respect to all the samples, right? So even in neural networks, you will see that the summation is needed when you are computing gradient. So you can still do the parallelization.
How about for example, the lasso or the ridge? Lasso and ridge, because when you have a
sure. But lasso and ridge are just penalty terms, and you can still do the optimization in the same way. Right? Yeah. Sometimes, I mean, see, when you really have 1 million records, there will be somewhere where you can do the parallelization. It's just to list the details of the algorithm. When we do it with 1,000 samples, we won't realize it. But as the increases, as the data points increase, you will see which points we need to move, which components we need to move.
Hello, Professor. I'm a PhD student from the University of Toledo. I just want to ask a question regarding a friend of mine. She's doing her MIS and MBA and looking at big data field in order to join it in the industry. I was just wondering what would your recommendation be as far as certifications are concerned? Which certifications do you